Of course, we have keynotes, so also I wanted to thank our keynote speakers for coming to Toulouse, who's not, well, it's sometimes not very handy to come to Toulouse, so thank you to these guys. And yeah, and of course the sponsors who are making the social event happening, because it's costing money and they're, giving us enough to make this also happen. So please, just before we get started, I got reminded that we got issues with personal belongings. We got some stuff in the university pretty recently. So if you could watch out your personal belongings or take them with you when you leave the venue to grab a coffee or anything like that, it would be nice, and we won't have to deal with such things. Okay, so now we're going to switch in French to introduce our first speaker. So Marc est conseiller régional, pardon, en Occitanie. Il est responsable du numérique et président de Cyberrock, et il va nous parler un petit peu pour ouvrir cette conférence. Merci, Marc.
Bonjour à tous. Je vais être très très bref parce que je sais que vous n'êtes pas du tout là pour écouter un politique vous déblatérer des choses politiques, mais c'est exactement ce que je vais faire. Donc je vais quand même être bref, rassurez-vous, ça va bien se passer, comme on dit. Alors, je vous disais, je suis conseiller régional en charge du numérique et ça fait plusieurs années que j'ouvre la THCon et c'est toujours un plaisir parce qu'en réalité, c'est un des rares moments dans la vie d'un élu où on n'a pas à faire semblant d'y s'y connaître. Vous y connaissez tous mieux que moi en cybersécurité, ce n'est pas le débat. Par contre, en tant que politique, je ne peux que vous parler des récentes évolutions du monde. Les récentes évolutions du monde, c'est quelque chose d'assez intéressant que tous les historiens militaires connaissent. C'est la question du coût de l'attaque par rapport au coût de la défense dans une guerre. Historiquement, vous allez à Carcassonne et vous comprenez que le coût de l'attaque était beaucoup plus cher que le coût de la défense. Quand vous construisez une citadelle, eh bien pour détruire une citadelle, il vous fallait beaucoup plus de moyens. L'invention du canon à la Renaissance, la diffusion du canon à la Renaissance, a transformé ça. L'attaque devenait moins chère que la défense. Et donc, quand l'attaque devient moins chère que la défense, ce sont des périodes de chaos. Il y a plus de guerres, parce que c'est beaucoup plus facile d'aller récupérer des territoires quand ça coûte moins cher d'attaquer. La réaction à l'invention du canon, ça a été le design des forteresses qu'on a appelé à l'italienne, qu'en France Colbert a importé, et la défense est redevenue un peu plus rentable pour les pays. Et donc, on a eu une période de stabilité. Le summum de cet échange, entre guillemets, du coût économique de l'attaque et de la défense, c'est l'arme atomique. L'arme atomique, le coût de la défense, c'est le coût de l'attaque. La destruction mutuelle assurée. Si la défense coûte autant que l'attaque, à ce moment-là, personne n'utilise l'arme. Et ça nous a donné une période de prospérité qui s'est globalement effondrée avec les tours du 11 septembre. Le problème aujourd'hui, et vous êtes au cœur de ce problème-là, et vous en êtes peut-être même responsable, je suis désolé pour vous, c'est que le coût marginal de l'attaque est devenu nul. Il est beaucoup plus facile d'attaquer dans le cyberespace que de défendre. Pour défendre un système d'information quel qu'il soit, il faut des milliers d'euros, il faut des personnes qui le sécurisent en permanence. Pour l'attaquer, il vous faut quoi? Soit un peu de chance, soit un robot, soit une expertise dans un seul des éléments. Si vous êtes spécialisé, j'en sais rien, dans les distributeurs de boissons connectés, eh bien, il suffit de trouver une entreprise qui a branché son distributeur de Coca-Cola dans son réseau pour pouvoir rentrer dans le réseau. Et quand je vous dis ça, on le sait tous, beaucoup d'entreprises le font pas attention. C'est sympa, c'est de l'IoT, ça permet des mises à jour faciles, on ne fait pas attention, et là, on a une porte d'accès. Et face à ça, face à ce coût marginal de l'attaque qui s'effondre, c'est responsable d'une grande partie du chaos du monde. Aujourd'hui, la question de la cybersécurité, elle est centrale, parce qu'en réalité, les attaques ne coûtent plus rien. Et là, politiquement, avec un grand politiquement au sens noble du terme, hein, c'est pas du tout partisan ce que je dis, c'est de droite comme de gauche, mais politiquement, on a deux solutions. Le déni, dire mais non, mais la cyberattaque, ça n'existe pas vraiment, la cybersécurité, c'est une coquetterie de RSSI, ou se dire, eh bien nous, on va prendre modestement part à ce combat-là. Et quand je dis prendre part à ce combat-là, c'est que l'attaque ne coûte plus rien, mais en plus, il y a un deuxième phénomène historique très lourd et qui est totalement contre-intuitif, c'est la démilitarisation de la cybersécurité. Si vous prenez Clifford Stoll, qui a écrit Le Nid de Coucou, je ne sais pas si certains d'entre vous l'ont lu, c'est un bouquin iconique des années 80. Clifford Stoll, il s'aperçoit qu'il y a une erreur de facturation de quelques cents sur un serveur et il va remonter jusqu'à des agents du KGB ou des services secrets hongrois. Bon, le livre reste sur le doute. Mais les cyberattaques dans les années 80, c'est essentiellement des problématiques militaires ou en lien avec des États. Ça a continué à exister, ça continue à exister, et on le sait aujourd'hui, il y a des grands groupes de hackers criminels qui sont en lien avec des États. Mais concrètement, parce que les cyberattaques sont l'activité criminelle la plus rentable, qu'on estime que le retour sur investissement d'une cyberattaque, c'est de l'ordre de 50, quand la traite des êtres humains, c'est 35, eh bien, on assiste à l'émergence de groupes qui ne sont absolument pas étatiques, mais qui sont uniquement mobilisés autour de la question de l'argent. Et donc, on assiste à une démilitarisation, on assiste à une suppression du vernis étatique des cyberattaques. Et donc, les cyberattaques, elles sont partout et tout le temps. Et donc, je vous disais, il y a une première version politique, c'est le déni de dire c'est pas grave, finalement, une cyberattaque, c'est comme un bug, ça arrive, mais c'est pas grave. Et la deuxième version, c'est ce que nous, on a choisi en région Occitanie sous l'influence de Carole Delga, c'est de dire modestement, humblement, il ne s'agit pas de dire qu'on résoudra tous les problèmes. On le sait. On sait que le niveau de menace, le niveau d'agressivité des attaquants est tel qu'il faut faire des choix, et il faut faire des choix stratégiques. Eh bien, faisons de la stratégie, accompagnons ceux qui, de près ou de loin, font la cyberdéfense et réfléchissent à ces questions-là. Et c'est tout le sens de la participation de la région à THCon, c'est tout le sens quand la région a par exemple construit CyberRock, que j'ai l'honneur de présider, dont les équipes sont là, vous pourrez aller les voir au café. On essaye modestement de permettre à ceux qui font la cybersécurité eh bien, de la faire la plus efficacement possible. On a la chance en Occitanie d'avoir des grandes entreprises de cybersécurité. Allez les voir. Tous ceux qui sont étudiants ici, quand vous cherchez des stages, eh bien, allez les voir. N'hésitez pas. N'hésitez pas, et n'hésitez pas même à être, j'ai envie de vous dire, et désolé pour les responsables de société qui sont présents, soyez exigeants dans vos stages. Soyez exigeants dans vos stages, ça veut dire faites ce que vous voulez faire. Alors je sais que là, si je vous demande à tous les étudiants dans la salle, vous allez tous me dire on veut faire du pentest offensif, grosso modo. Est-ce qu'il y a des gens qui ne veulent pas faire de pentest offensif? Non. Bon, il y en a quelques-uns qui mentent, mais c'est pas grave. Bon, on a quelqu'un d'honnête. Quand je vous dis allez faire, quand vous allez chercher des stages, quand vous cherchez votre premier emploi ou votre deuxième emploi, il existe des centaines de métiers dans la cyber qui ne sont pas forcément du pentest offensif, mais qui sont tout aussi intéressants, voire plus intéressants. Et vous êtes collectivement, et je le dis sans flagornerie, et j'en terminerai par là parce que j'ai déjà été un peu rapide, enfin j'étais un peu long, pardon, vous êtes notre première ligne de défense par rapport à ce que je vous décrivais. C'est vous qui demain devront collectivement apporter une réponse à cet ancien problème qui est celui de la cybersécurité. Et cette réponse, elle peut être que nouvelle. Il faudra trouver de nouvelles façons, il faudra trouver de nouveaux moyens, et il faudra, entre guillemets, hacker le système pour s'assurer qu'on ait une réponse à la cybersécurité. Alors, en conclusion, je crois que l'année dernière, j'avais cité Linus Torvald, de mémoire. Ouais, les politiques peuvent citer Linus Torvald, parce que Linus Torvald, à la fin de son livre, il disait, grosso modo, si une civilisation extraterrestre vient et nous demande, il nous dit, grosso modo, Nusterwald, les innovations, elles passent toujours par 3 stades. Le premier stade, c'est la guerre. Les innovations sont portées par les militaires. Le deuxième stade, c'est le prestige social. C'est l'idée que les innovations sont portées pour augmenter le prestige social. Prenez l'iPhone, par exemple. Et le troisième stade, c'est l'amusement. Le dernier stade de toutes les innovations technologiques, c'est l'amusement. On a inventé la voiture pour la guerre, ça a été une question de prestige social, et on a inventé le karting. Et Linus Torvald, il disait finalement, si une civilisation extraterrestre vient, moi la seule chose que j'espère, c'est que la première question qu'ils nous posent, c'est « venez, on va s'amuser ». Ça voudra dire qu'ils seront post-modernes. Alors je ne sais pas si une civilisation extraterrestre viendra, et je ne trancherai pas cette question devant vous, mais en tout état de cause, aujourd'hui sur la cybersécurité, on est au premier stade, et peut-être qu'au-delà des CTF, au-delà des captures the flag, à terme, parce que tout le monde travaillera dans la même direction, dans quelques années, on regardera ça comme un grand amusement. Je vous remercie.
Okay, so thank you, Mark, for this nice introduction. It's time to open the conference with the first keynote speaker, who is Matthias Payer. He's coming from Switzerland. He's a professor at École Polytechnique de Lausanne. Yes, it's French. He's also a French speaker. So if you want to speak both French and English, you can try. And yeah, so Matthias' interests are research interests are about building secret systems on unsecure software and hardware, if I can summarize it like that, if it's okay for you. And he's also leading Hex5, security research lab or organization, is it? I don't know. Hex5, yeah. And today is going to discuss about Android cybersecurity, and at the different levels, both on the with this angle, the offensive angle, the defensive angle, and with, I guess, fancy stories to tell. Thank you so much. You can take the floor. Thank you.
Awesome. Thank you very much for the introduction. Bonjour à tous et toutes. Je parle français seulement un petit peu. Alors, si vous voulez demander quelque chose, vous pouvez faire ça en français, mais la présentation est en anglais. I'm going to talk about Android today and a little bit of research we've done in the Android ecosystem the last couple of years. Obviously, this is not work that I did just by myself, but I'm actually working with an amazing team of researchers at EPFL. And one of the reasons why I'm giving this talk is to actually present you the EPFL as a research opportunity, and you may want to join sometime down the road. So let's look at Android for a bit. Quick show of hands, who has an Android phone? Okay, that's about 80%. Who has too much money? So who has an iPhone? Just for completeness. Okay, about 10%. Usually, if I ask this in Switzerland, it's about 50-50, and not 80-10 with 10% abstentions. In Switzerland, so it's 50-50, even for students, right? But in general, a lot of people actually have Android phones. And when we're looking at the Android ecosystem, we see that there's massive amount of complexity, a crazy amount of complexity. We have 3 billion users across 190 countries. Android overall has a 75% or 3/4 market share for all the mobile phones, so this is massive, right? We've got roughly 2.6 million apps in the App Store, another massive amount of complexity, and 1.5 billion devices sold per year. And we somehow have to secure this ecosystem. So while Linux on the desktop kind of failed, at least Linux succeeded in the mobile environment. And we went out on a journey to analyze this ecosystem. And somehow, like a couple of years ago when we started this, we accidentally downloaded a couple of terabytes of system images and firmware images from different vendors. And we looked at the Google Play Store and tried to download a few apps. Our script was wrong, and we ended up with 11 terabytes of apps that we downloaded, right? Accidents happen, you know? And after having this large treasure trove of firmwares, of apps and whatnot, we started analyzing it to figure out how this ecosystem actually looks like. I've seen that already a lot of you are using Android on their phones, but let me just give you a very quick overview of the Android ecosystem and the security of the ecosystem. You have your phone, right, that actually runs a bunch of apps. That's Google Pay, Netflix, WhatsApp, Signal, Duolingo if you want to learn French or German, whatever rocks your boat. And you've got the other side, the trust zone side, that many of you will not be that aware of. But from a security design perspective, it's actually a pretty clever approach to move some of the very trusted applications into a separate, isolated compartment that is hardened and with a couple of very hard and tight security guarantees from the runtime ecosystem and from the underlying hardware. And all your very private personal data, like fingerprints, keys, some very private information is actually stored in this trusted world. And we've got the normal world and the trusted world. And obviously the two worlds need to communicate with each other, right? So there needs to be some kind of information exchange. And I've already alluded a little bit to this from an attacker model. The normal world is supposed to be compromised. And we want to protect the trusted world from any kind of attacks from the normal world. This could be due to malicious apps that you install, right? Maybe you see, oh, there's a free app that does everything the paid app does. I'm only giving the attacker code execution on my device as a trade-off. Right, so you may be running a malicious app by accident, and the user is not supposed to know the difference between a malicious app and a normal app, right? So the malicious app has access to anything that the normal app has, but there could also be bugs in the applications that could be exploited from afar. But that's not all, right? There could also be bugs in the trusted application that are running on the trusted side of things. And one more thing, right? That's not all either. There could also be bugs in the communication channel between the normal world and the trusted world that we want to look at. And this sounds all very technical and very boring, so I'm gonna change gears a bit, because for any interesting talk, as you know, we need to have a storyline. And I'm gonna date myself a little bit. I'm gonna take you through a journey across Middle-earth. And we're gonna explore a couple of places in Middle-earth. We're gonna start in the Shire, where things are rosy and fun, right? We're gonna live in a world of plenty and see what we can actually do there. We're gonna journey and see what the dwarves are up to in the mines of Moria. And we're gonna dig really, really deep into the systems layers. Then we need some like rechoice and rejuvenation. We're gonna see the elves and see if they can offer us any lembas. We're gonna explore Rohan and see what's there. And finally, we're gonna go to Mordor and explore whatever happens there to see our journey end. So let's start in the Shire. Things are rosy, right? Things are plenty. And we're looking at Android trusted applications to start with. And when we started looking into this ecosystem of the couple of terabytes of trusted applications, of systems that we had, we kind of wondered, like, how secure are they? Can they be compromised? And what's the update strategy that vendors actually have? And who's playing CTFs? Quick show of hands. Right? Who's familiar with the term of cheesing a challenge? Okay. For the rest, I'll quickly explain. Cheesing a challenge is finding an easy, unintended solution to a tough problem where you're just quickly solving the challenge in a very unintended way. And this is pretty much what happened when we started looking at Android trusted applications. We assumed that, like, our initial hypothesis was we're going to build a large cluster of different systems. We're going to collect all the trusted applications. We're going to build a fuzzing harness. We're going to fuzz. We may find bugs. This is going to be complicated. It's going to take years. Then we started looking at trusted applications. Now, but also to understand how trusted applications work and what the security profile is, let me quickly explain what it's supposed to do. Right? We've got the normal world, remember, from the initial picture, and the secure world, the trusted world. And the trusted applications, they are loaded from the normal world into the secure world, into the trusted world, right? So trusted applications are moved from an attacker-controlled space to a secure space where they're being executed and have access to very sensitive data. Now, obviously, this needs to be signed, right? We need to sign the application so that the trusted side can actually check the signature and make sure that it hasn't been tampered with. Now, so far so good, but unfortunately, these trusted applications can have bugs. And vendors will update the trusted applications. Now, the issue is, like, we have two versions of the trusted application, the updated version and the old version. And unfortunately, due to rollback attacks, right, an attacker that has access to the user, like to the normal world, can actually just load the old buggy version and thereby exploit the bug even after it has been patched. What's the obvious solution to this? How can we mitigate this attack vector? We can have allow list, deny lists with, what did you say? With vulnerable versions. Yeah, how do we update those? Right, anything is being pushed from the, say again? It's the same problem. Yeah. You're kind of close though, right? That was a very good answer. We add version numbers. Like instead of having an allow list, deny list, we're going to have a version number for each of the trusted applications, and we're going to bump the version number every time, or the rollback counter every time we update the system, right? And now, when the attacker tries to load the old version, like version 1, the signature will actually still be okay, but the version is too small, and therefore the trusted world will reject the application. Now, this is obviously being done, right? Well, the system is implemented, right? The system is there. The vendors are using it, right? So we did a large-scale study, and we analyzed the prevalence and use of rollback prevention. We picked 5 OEMs, which correspond to around 65% of market share over the last couple of years, and looked at all the firmwares that we accidentally downloaded. We group phones by device manufacturer and pick several phones in the group. We extract all the TAs, analyze it. We end up with 35,000 TAs and versions, out of which around 300 were unique across 4 TE implementations. We looked at rollback counter extraction and then measured when and how trusted applications actually increment the rollback counters. We then correlated this as a public vulnerability review, where we kind of like looked at what are the CVEs actually filed against these trusted applications, how are the update strategies being coordinated and whatnot. And overall, we found 2,500 vulnerable trusted applications and 190 rollback counter usages or increments. Now, you don't need to be good at math to see that the two numbers are different, right? And then we analyzed and looked at all the different systems. If you want to know all the gory details, I invite you to look at the paper. But we actually discovered that there's several vendors that are doing a pretty terrible job at incrementing their rollback counters and keeping all the different parts up to date with very questionable TA vulnerability practices. So like one large vendors where the phones usually start with an S or an A, actually has different teams working on different trusted applications. When they start a new phone, they just take the code from one team, clone it, and let the other team run with the code. So vulnerabilities across different phone models may actually still persist. They may be patched in one and not in the other. So when you're just disassembling or diffing the code between two different phones, you can detect different vulnerabilities. But to make things extra fun, they're using the same signatures for the two phones. So you can actually cross-load application between phones to exploit the underlying system. Because why not, right? This is certainly a feature that that an attacker absolutely needs. There's also quite a bit of lack of transparency regarding the TA rollback prevention. They're not really talking about this openly or even disclosing vulnerabilities. With a lot of vulnerabilities being patched silently by teams as data is being merged, and then if you patch a bug locally, you don't need to increment the rollback counter, right? Well, you actually should. If you don't increment the rollback counter, somebody can still install the old version and just exploit your system. So we actually did this and published this last year at Usenix Security, but we also did the hard stuff. We also built a fuzzing pipeline for trusted applications in Tease, where we implemented a way to fuzz custom trusted application on custom off-the-shelf Android devices. We analyzed the client application in the normal world to extract kind of usages and like interfaces to the trusted application. Analyzed the interface, recorded some seeds, how benign applications were interacting and interfacing with the trusted application, and then built a fuzzing harness to go find bugs. And obviously, we found bugs in trusted applications as well. The fuzzing pipeline is open source, same as with the rollback counter metadata. So if you want to use that in your future research, feel free to do so. Now, we know that trusted applications themselves are buggy, right? What else can we do? Well, we decided to go dig a little bit deeper. And we wanted to explore how the different systems interacted with each other, how the normal world was interacting with the secure world, and how the interfaces were actually managed. Like, how does the secure world interface and protect itself against the normal world? And by the way, when I was looking up quotes for this talk today, I finally learned why AI tools, why ChatGPT is always using Delft. Right? If you haven't noticed this, ChatGPT and other LLMs always use the verb Delft that I've never seen in any other text. Looking at this, Delft was a very common word in the 50s. And it was learned, like LLMs have been trained on all the different texts that exists without a distinction between time, right? So if you look at 50s text, it's going to be much more common, but not today. So yeah, we're going to go deep and dig into the secure monitor, right? You've got the normal world here that's separated and isolated from everything else, and you've got the secure world there that is running the trusted application, the trusted OS, and so on. And to communicate between the two, you have the secure monitor that sets up any kind of interaction between the normal world and the secure world, right? The secure monitor may also set up page tables to have a form of shared memory, so you can actually have fast communication between the two sides. But for anything that you want, you need to do a SMC, like a secure monitor call, which traps from the normal world into the secure monitor and then down into the trusted side of things. What we started wondering is, well, how secure is the secure monitor actually? Because this is the most trusted component in the Android ecosystem. If you have a bug in the secure monitor, it's game over. Right? This is literally game over. You control both the normal world and the secure world. You control everything, right? You have a complete takeover of the system. This is the most trusted component. So I'm in France here, right? So for sure this is formally verified. Right? For sure this is thoroughly tested. For sure there's not a bunch of crap in there that you don't need. Well, we wanted to look at that, but it's kind of hard to analyze the secure monitor. And there's a bunch of like challenges that make this a bit more difficult. First off, you have very limited introspection capabilities. These secure monitors are running deep down, locked down on the phone, and it's not easy to emulate them, right? So when you want to rehost this system, you actually need to take care of a bunch of constraints for how the system accesses the underlying hardware, how it accesses other software components, how it interacts with the rest of the system, right? So you cannot run this on the phone because you don't have access to it, and it's not easy to rehost because of all the different low-level hardware constraints and low-level hardware dependencies between the the different peripherals that the system is running, and yeah, the different software component that is interacting with all the proprietary services. And we were interested in just fuzzing the secure monitor, not rehosting all the different applications that it was relying on in addition to that running in the trusted world and in the normal world. And it's also a very complex input space, right? If you look at the SMC instruction, right, you do an SMC call into the secure monitor. The first register contains the function ID. And there's like many different runtime services with very unique APIs that we have to disambiguate. And we've got a 64-bit number to select the different function IDs, right? This is extremely difficult to keep track, and also a very large state space to actually fuzz. So what we did in Elixir, we developed a system to fuzz these underlying systems. We developed a process to snapshot a booted secure monitor from a system. Then for any kind of peripheral access, we do reflected peripheral modeling. And then we define a fuzzing harness to explore this. But let me break this up into a bunch of different states. The first contribution is a partial rehosting of secure monitors. And here we took inspiration from the informal security, from the hacking community, where usually in an academic approach, you would invest like 2 years of a PhD student to develop an automatic approach that a human analyst could do in a day. And sure, you could write a paper about the way how you automate this, but in my group, we're trying to make sure that it actually needs to make sense, right? We don't want to invest 1 year of a PhD student just to develop a system that is doable by a human analyst better in less than a day, right? So the first contribution here is a model of how we can partially rehost systems. And our emulator actually supports you as a human analyst to rehost. Right? You start booting the secure monitor, and when it traps, you set up all the different registers, different connections and whatnot, so that you can actually bring this up to a state where it is running. And it's like an iterative approach with a human in the loop that patches all the missing components, until we get to a point where we think the secure monitor is reasonably booted, and then we take a snapshot from there. If it turns out that the snapshot is not good enough, you can always refine later down the road. So far so good, right? We've got a snapshot of the secure monitor, a memory snapshot of this, and state snapshot of the secure monitor that's somewhat booted and has some control over the system. We can now execute SMC call into the systems. Now, the second difficulty that we are facing is that this secure monitor actually relies on a lot of low-end peripherals. And like, I don't know about you, but I don't want to spend a couple of years re-implementing Python stubs for every single weird peripheral that this system is using. So we figured the best possible approach is just to let the fuzzer handle this. And we defined the fuzzing input, the first part, to explore the secure monitor itself, like to fill all the data for the SMC call. And all the remaining fuzzing input is whatever is being read from MMIO watch points that we have set up in the first step, right? In the first step, we tagged all of these entry points are MMIO watch points, and now the fuzzer can feed all the input into these MMIO watch points and actually get this going. And that way, we can actually start fuzzing the secure monitor and see what's happening. Last but not least, we need a harness synthesis, right? We need to have a good driver. We need to understand what kind of functions are being used, what kind of parameters are being used. And for this, we just analyze the source code of the rich OS, which is open source, right? So we scan all the different code. We figure out the ways it interacts with the secure monitor. We collect we essentially build a dictionary of parameters, of calls and whatnot. And then we can actually use this to fuzz the snapshot of our booted secure monitor, and the fuzzer naturally fills in all these MMIO watch points. We targeted 7 different targets from 6 different vendors, 4 of which were open source, so that we could do a ground truth validation, and a bunch of closed source systems. We found 17 security relevant bugs in 5 targets, including a bunch of different vendors. Especially, I want to give a shout out to the phone vendor where all the devices start with S or A. They managed to group 5 distinct bugs across different phones under a single CVE, which if you ever learned about the definition of what a CVE is, it's supposed to be a unique identifier for 1 bug, not one identifier for 5 bugs. But I guess that way they reduced the pressure on the team for all the security bugs that were found in the secure monitor. Looking at the evaluation, right, I'm still an academic. We need to show that we are better than everybody else, and we have higher coverage, yada, yada, yada. Things are good, but we also find bugs. So let me summarize for Elixir, right? So this is a fuzzing approach for secure monitors, both open source and closed source. Key idea is to take a snapshot of the system, use reflected peripheral modeling to feed in data to all the MMIO watch points, and then figure out a good harness by analyzing the source code. System is open source, fuzz your own secure monitor. We would be very happy if you gave us feedback for that. We're going to do a quick detour from our story and talk about communication platforms, right? There is a way how we are interfacing between the normal world and the secure world, between the trusted applications, right? Normal world with regular applications and trusted applications on the other side. Now, this communication protocol needs to be secure. You need to be very careful in whom you allow to join the jet and who is allowed to interface and interact. Now, again, here we've got the same image as before, right? We're not searching for bugs in the secure monitor, but this time we're wondering about bugs in trusted applications. We already fuzzed the trusted applications in the first space, like in the with T's that I presented before. But here we actually observe that, well, all the trusted applications, they actually follow the same API. And this API is called the Global Platform API. Who has looked into this? Quick show of hands, please. 1, 2, 3. So if you ever cannot sleep at night, I recommend looking at the Global Platform API. It's almost as good as the Bluetooth specification, right? The Bluetooth specification is still far out there, but Global Platform is getting close. It's similar to the Bluetooth specification, like a death by consortium with like 50 different vendors trying to merge all their different standards together, making this a massive, humongous mess. That's also extremely complicated. Now, I'm going to indulge you a bit into how this Global Platform API looks like. Let's say you're an application developer, you're programming a trusted application. This is pretty much the blueprint of how you handle a function in a trusted application. Right? So you're writing a little bit of code, you're the application developer, and think about the context, right? The runtime system called, like the user space app issues a call, the system orchestrates, and then like this ends up calling this, like along the chain of command, you end up calling this function in your trusted application. And we're going to see how the system actually develops. And you're the application developer writing this app. So let's look at things, right? First parameter, this is the session state and the session context that contains the necessary information. This is the command ID and the handler that is being used. This is under the attacker control. Then there's the parameter types, which determines the types of the parameters. If the type is a memref, then the runtime system validates buffer location. So if the attacker selects that this type is a memref, then the runtime system will validate the reference. Remember this, right? If the attacker selects that this is a memref, then the runtime system will validate the buffer location. And then we have 4 TE parameters. And how do these TE parameters look like? What's the worst thing you could do for security? Anyone? You make this a union, right? And a union between two structs. And it's either a buffer and size, or it's 2 in 32s, right? Because this is pretty much the dumbest thing that you could do as part of your API design. This is perfectly fine, right? The attacker decides what is being done with the parameters, and decides if this is a memref or a regular type. Now, let's see how this actually becomes exploitable, or what the underlying issue is. Right? We now know that these are the parameter types. And now, the good thing is, right, as a programmer, you can check. Like, you can enumerate the different parameter types and ensure that if the parameter types that the attacker set are not the parameter types that you expect, then you just return bad parameters and you error out. Awesome, right? Otherwise, you continue with your program. And then you access the memory locations. Now, you know what? This is optional, right? The type check is optional. But of course, the application developers all remembered to have this type check in their code, right? Well, unfortunately not, right? And if you think about an application developer, it's fairly easy to forget. You're writing your function, right? You're not aware that you're running in a trusted context, right? You're just programming an application. You're just hacking code and you're trying to get your functionality together. And you're not aware that somebody could be sending wrong arguments, because this other team is writing the interface from the normal world that is calling into you. You can maybe get a couple of unit tests, a couple of test vectors, and you're just running your function on your end, right? You're not aware that the attacker could just provide different arguments. So what did we do? We wrote a quick Ghidra script that disassembles the trusted applications, looks at these entry vectors, and checks if the parameters are used correctly. And if they're not checked, like if there's no parameter check, then we simply alert, hey, you may want to look at this application because this could give you an arbitrary right in a trusted application. So let me explain this in a bit more detail, right? Here we've got a simple example application with a TA invoke command entry point. Parameters are here. They flow into the values here, and then are used as values A and B. Parameter types are being passed along as well. They're not being checked, but this is not an interesting function. So nothing happens here. This is fine. Like there's no exploitable use case. Now instead here, again, we have the parameters that flow into the function and are being used as a memref.buffer. And we've got the parameter types that flow and are not checked. But this is interesting, right? Because now we have the runtime system that, based on the parameter types, will check that the buffer is present, the buffer is mapped. Otherwise, if the attacker sets, oh, type value input, this is not a memref, this is just a regular int, then the runtime system does not validate the buffer, but the code of the trust application still accesses it, which gives us immediate arbitrary reads and arbitrary writes in trusted applications through this API, with a little bit of fudging. Now, that's clearly a serious issue, right? And it should be, the check should be mandatory and orchestrated by the runtime system. We scanned the complete TA ecosystem. Roughly 7,000 apps that we have, trusted applications, are global platform compliant with 131 unique trusted applications. 850 or 33 unique vulnerable trusted applications were vulnerable to these parameter confusion. 9 were publicly known, right? Somebody else found those issues while we patched. 10 were silently patched. Remember the rollback attacks and the counters, the rollback counters that were not increased, right? These applications are part of those as well, right? So you can just reuse them for your future exploitation needs if you ever need read and write access in a trusted application. And we also found 14 O days and a bunch of CVs. Right? Maybe a quick note for this conference, we always responsibly disclose, even though it's often very, very painful to work with the vendors to actually get these bugs fixed. We then worked on a mitigation. Right? It's obviously extremely stupid to have this fail open design that you trust the application developer to check that the parameters are correct. And we proposed, instead of a fail open, a fail closed design with a mandatory type check, where the programmer registers, when you register your command entry point to the runtime system, you tell it, these are the parameters I expect, and nothing else is possible. Right? So the runtime system can reject, and not your programmer code. We actually sent the proposal to global platform. The update is in progress, and they are changing their API based on our suggestions. So if we're burning your O days, I'm sorry about that. But I think overall this is an interesting change. Now, global platform was very open towards discussing with us until we actually named this global confusion, and then kind of the communication slowed down a bit. But it was a fun experience on actually working in this ecosystem. So far so good, right? We've looked at the trusted applications, secure monitors, and whatnot. Let's take a bit different journey and look into the normal world for a bit, right? And we're now gonna explore the regular Android normal world regular applications. And securing applications is hard. We need mitigations, we need different kind of testing, we need to update the libraries that we are using, and so on, right? This is really, really hard. We don't want to do this, so we're just gonna slap a secure allocator on it and everything is fine, right? Who knows what allocator Android is using? Anyone? So, Android uses Scudo, which is a hardened memory allocator designed for security. Right? It's a user-space memory allocator with the only key goal to prevent exploitation of heap-based memory corruption vulnerabilities. In Android 1, we had DL malloc. In Android 5, they moved to JE malloc. And since Android 11, we actually have Scudo with a security-first approach. And we wondered, is it really secure? The design principles are really nice, but do they hold under Android? So let's look, right? When you're exploiting an allocator, you've got the application, which is malloc and free, that are being passed into the memory allocator, and the memory allocator kind of manages all the heap memory by breaking the heap memory into chunks and giving the application a different chunks for heap memory. We assume that the application has bugs, and the application contains heap vulnerabilities such as an overflow, use after free, double free, whatnot, which are usually very, very hard to work with, and they are a bit cumbersome to write exploits for. So when you want to exploit those, you usually, like when you have an overflow, use after free, double free, or whatnot, you try to leverage this to corrupt inline metadata of the allocator, and then by reading the lore, you will understand that you can adjust these parameters of the heap allocator state to then turn these into arbitrary reads and arbitrary writes. So using the memory allocator as a confused deputy, you can turn different kind of heap vulnerabilities into arbitrary reads and arbitrary writes. So much stronger primitives. And we were wondering if Scudo allowed some kind of corruption, some kind of reuse of these, re-implementation of these techniques, even though Scudo was hardened against all of these attacks and should protect against these attacks. And for that, I need to explain you for a second what Scudo actually is. I think nobody has heard of Scudo before, right? So, even though you're all running Scudo on your phones. So Scudo is very, very clever. It uses randomization to randomize the address of allocations. So there's a random key that on the heap shuffles the allocation. So for each run, you will have a different placement of all the different memory objects that you're allocating. But not just that. Scudo protects inline heap metadata. Right? All the chunk headers are signed. And Scudo verifies the signature before parsing the metadata. Right? So all the metadata that is in line with the memory blocks is signed and checked for different security parameters. If the signature check fails, Scudo aborts. Amazing, right? Now, how can we exploit this on Android? Or does anybody see the issue with Android userland? The signature is always checked. Say again? How? This is correct. Why is this the case? What's the key? Go ahead, just talk. Yeah.
Contents and the size and the expected English one is the same to the other.
Yeah, but it doesn't matter. That doesn't matter. The issue is that the key is the same. Why is the key the same?
Maybe because the header is not related with what is the contents of the block.
No, it's about the key. Let me solve the riddle. Android uses a performance optimization. Who knows the Scudo process? Right? For everybody working on Android userland, Android doesn't have ASLR. What Android does is, when you start the phone, it preloads the runtime environment. And to make application startup snappy and fast, it just forks. It doesn't execve the new process, it just forks. Right? So all the memory map is the same of the old process. Right? So this is the exact same image, which means the Scudo process, which is the root of all the Android runtime systems, just forks between the evil app and the victim app. So the ASLR layout between the evil app and the victim app will be the same. But so are the Scudo secrets, such as the randomization key and the protect secret key. Right? So an attacker only needs access to the actual, to an app to read the secret values and then attack another value. Now, the evil app can be your shitty, unprivileged, zero privilege app. The victim app can be your system service. Just think about this, right? Your system service is running with the same ASLR and Scudo secrets than your whatever shitty instant app that you're launching over the web. Great security design. So ASLR and Scudo secrets are shared, which is obviously not great. We demonstrated that it was possible to exploit a heap underflow in the system server by just porting this very cool CVE from 2015 to Android 14, which is a heap underflow and overflow. And then this allowed us to exploit from an unprivileged instant malicious app over IPC the system server and get the code access there. We had this at Wood last year. So check out the code and the paper if you're interested in more detail. And how would you solve this? Right, how do you solve this issue? You start a new runtime system each time, right? Has anybody heard of Graphene OS? Yeah, so Graphene OS starts a new runtime environment for each app that you start. That's the only sane option. You lose half a second of startup time because you need to reinitialize the runtime system for each app, but that's the only sane solution. And now, the thing is, right, there were teams at Google implementing Scudo, and they were really, really clever, right? The design is really good. But in the Android environment, due to the constraints of the environment, Scudo is more easily exploitable than old allocators, because old allocators did sanity checks do the pointers that we are looking at roughly make sense because of possible overflows, right? And now Scudo does a signature check and just trusts. And you get much more powerful primitives thanks to Scudo than you would get through the old allocators. Right? And this is what happens when teams, security teams, don't talk about each other. And this is why it's so beautiful to look at security. Now, last piece, right? We've gone through a very extensive journey, and we are still looking at Android user space applitions. And we wanted to look in like, what do these applications actually do? What kind of libraries do these applications use? And we had an amazing 5-step plan. So this research started about 2 years ago. We download some APKs. We build a binary similarity thing to analyze all the different libraries, to detect custom patches in libraries, to detect versions in libraries and whatnot. And they're for sure vulnerable, bad vendors. Bad, we're going to disclose, we're going to make a lot of money in bug bounties, we're going to be rich, the student is going to graduate and go on to a faculty position, they're going to be super happy. We never got past step 1. And let me take you on the journey of this path for a bit. So we wanted to construct a data set for ground truth validation. And for that, we scraped diverse markets such as the Play Store, Playdrone, AppChina, Anji, Me.com, F-Droid, and whatnot. And we got 8.7 million APKs. Around 1 in 8 has native libraries. And we ended up with 1 million unique libraries. First discovery, right? A lot of code is actually shared. And if you think about, right, all the academic binary similarity papers are like, we build a tool and whatnot, and then scale across all the different systems. What we found is, well, a lot of the code is just shared. Now let me think a bit. Why is this shared? Top 50 binaries account for 14% of native libraries. Top 5,000 binaries of the pool of 1 million accounts to 78% of all the native libraries. So there's a lot of code sharing going on. Now, why is this the case? Now, how do we infer the library names and the versions for all of these tools? We're going to use machine learning. There's amazing machine learning tools out there, very complicated, very amazing. They claim to be the best. There's every security conference, there's a new machine learning tool that applies better algorithms and scales and does whatnot. We looked at their performance and the pool size, like how many libraries can they distinguish? 10, 100, 1,000, 10,000, right? What do you observe? On the x-axis, we're going from 1 library to 10 to 100, 1,000, 10,000 libraries. We did ourselves a very sophisticated machine learning approach to extrapolate on how this will progress with larger pool sizes. And our amazing machine learning approach told us that it's going to get down to 0 pretty soon. What we discovered is that machine learning works great for small data sets. In their papers, they usually use toy data sets of 350 binaries. It takes 12 hours to create the embeddings on a machine learning side of things. Our data set with 1 million libraries would take around 40 years. Right? So the pool of libraries that machine learning is playing with looks a little bit like this, right? Which is great for kids. The pool that we are looking at the Android environment looks a bit like this, like 10 Olympic pools. Which is, we're talking about a slightly different problem here, right? Both problems are fun and can be lots of fun, but there's some differences. So we started evaluating our data set a bit, and we looked into library reuse. And we saw that a lot of libraries were actually reused across many apps, and then unfortunately never updated. So as it turns out, developers just download tarballs and zip files, dump them with native code, dump them into their project directory, and then leave it there forever. So we have found several apps, even very well-known apps, that are vulnerable to CVEs that are 10 plus years old. For that, we need some ground truth, right? We looked at Maven, which is a main source of packages that people download. With a little bit of heuristics for React Native, we get around 60% of matched libraries. and we can recognize the 60% of libraries, no need for any AI. So we got rid of the expensive AI solution, and the student couldn't publish because SHA-256 sum was better than any AI solution we had. Which is a very unfortunate result, right? From an academic perspective, you can't publish that your SHA sum is better than whatever machine learning solution the other people came up with. But we looked a bit at vulnerabilities in these libraries. Who knows droids on droids? Like, this was a very, very well-known vulnerability in 2019 that WhatsApp was even vulnerable to. And as we found out, 45,000 Android apps still use this library. How many remain vulnerable? Well, around 80% of apps are still vulnerable to a 6-year-old CVE. If you're looking at the Play Store, that's about 60% of apps that are still vulnerable. Now, vulnerable does not mean exploitable, right? So if the GIF image comes from a trusted server, this could still be okay, right? So we didn't analyze exploitability, but it's vulnerable to this bug. Let's look at the top 3 apps that are still vulnerable to this CVE, to this very old CVE. Well, there's the screen recorder, 143 million downloads. There's Paint by Number, a coloring game, 242 million downloads. And 400 million downloads by this other kind of weird company that is shipping this app by default, right? And again, exploitability, vulnerable does not mean exploitable. We're only highlighting that the vulnerable libraries remain used. So what else am I doing, right? We are the HexHive Research Lab. We're doing a lot of research across the whole software ecosystem and system ecosystem, not just Android. We do software testing, where our goal is to find bugs before others do that, mostly to help developers, but also to help hackers find more and interesting vulnerabilities. If you're interested in that, talk to me during the break. We've been working on mitigation. So if you know Shadow Stack, Safe Stacks, or CFI, we've done quite a bit of work on that. Going forward, we're also looking more into compartmentalization. My research group, like I couldn't have done all of this research myself. I actually work with a lot of talented students, postdoc, and master students. Join us on this research journey. EPFL is an amazing place. I always enjoy hosting visitors. They come for a talk, for some discussions, or just to join me on a ski day somewhere up on the slopes, which is kind of cool. So let me summarize. Right, Android developed into a very, very complex ecosystem. It has many different layers. So the security remains an elusive target and it's hard. The good thing is there's per app compartmentalization. Sensitive data remains in a trusted world. But there's bugs in the hypervisor, which is kind of what we expected, right? Any complex system will have bugs. There's a couple of things that are unnecessary, such as vulnerable communication APIs. There's terrible things like forgetting rollback. Developers are only slowly catching up on that. There's even the naive, where unsafe allocators create new attack surfaces, and the crazy reusing libraries without any kind of updates. So I hope you enjoyed this journey across the Android ecosystem. I'll be around for the next 2 days. I'm happy to take questions now or any time during the next 2 days. Thank you very much.
Thanks. So we are late, but we have time for 1 or 2 questions.
Don't be shy. Yeah, I guess I'm going to start with 1 question. Yeah, any question? No, okay. Yeah, it's over here. It's me. Yeah, so I was wondering about the fuzzing, the fuzzing paper you did present, and more especially the MMIO mutation. And so I was wondering how much so of course, did you try that, these bugs you did find on the real systems and see how the MMIO space were actually constrained and if it were matching, or not?
We mostly did dumb shit, so this was not, it was not clever. We just let the fuzzer explore. And the feedback that we get from the system kind of reflects what the real peripherals are doing. We have an ongoing project for embedded systems. Think your Bluetooth peripheral, like the Bluetooth chip, the Wi-Fi chip, the 5G chip, that is looking at better analysis of these peripherals. But for the secure monitor fuzzing, dumb fuzzing was all that was necessary. The secure monitor was good enough to like just react in a reasonable manner. Now we could have false positives, as you said, right? There could be wrong data back, but we replayed all of that on real phones, which gives us information if this is a true crash or not. Right. So short answer: we filled it with garbage. Was good enough for a secure monitor. We're working on better systems for others.
Yeah. Thank you.
Thanks for the talk. So I want to get back to the rollback, the lack of anti-rollback, basically. Do you only explain that through laziness or maybe skill issue, or might there be some kind of corner cases where a developer might not want to check for rollback in order not to break the system, for example? So yeah, or maybe technical issues, having lack of temper-evident memory, stuff like that.
Yep. So rollback is hard. Rollback is really hard. Like I downplayed this. Getting rollback right is very hard. Now, for a single phone, let's assume you have permanent storage for the rollback counters. For a single phone, this is fairly okay. Now, but you have ODMs, OEMs, and whatnot that share applications across different phones, across different vendors and whatnot, which makes coordination for the rollback counters extremely challenging. And you have leaks between vendor A and vendor B, right? Because vendor A may have already patched, while as vendor B is a bit slower, right? So you still have this race where you could attack an application that has increased the rollback counter on vendor A, but not on vendor B. Or inside a vendor, right? Between the S phones are usually updated much faster than the A phones. So you can actually use information for whenever the S phone increases the rollback counter, you can exploit all the A phones for another good 6 months or so, right? Because they're much slower in their uptake studies. It's really hard to get this right because code for the trusted application is shared so broadly and widely. Or you can also do the Google approach, right? Google just doesn't do rollback counters, but they have a different mitigation. You're only allowed to load trusted application from the system partition, which is read-only, which kind of limits you. You can only update trusted applications whenever you do a large system update. So there's a lot of different trade-offs. There is no easy solution. Yeah.
Thanks.
It's a hard and challenging problem. But yeah, teams should talk to each other, right?
Sure.
And coordinate.
Thanks.
Cool. Thank you.
No questions?
Okay.
Very cool. I'll be around
Yes,
in the breaks
the
and
break.
whatnot, so feel free to talk to me one-on-one if this is too intimidating.
Okay, thank you. Thanks a lot, Matthias, again.
Thank
you
you.
so much.
Thanks. So we're going to switch to next presentation. Guys, presentation for Pierre Ayoub and Aurélien Hernandez from Oricom. They're going to talk about phase-modulated emanation inside channels. So they use their own laptop, so just check that.
Intel products where the only last line of defense is that MMIO has a specific structure. Because we have we cannot afford defense in depth due to performance issues.
Yeah.
And this is this is why I was wondering if
It's pretty cool. So this would be a fun
yeah.
approach to actually collaborate, to be honest. No, if you're interested in that, right?
yeah sure or what software are you talking about? You know any case
Internal?
yeah also internal. Yeah we I have some examples in
The question is depending on a good peripheral lab or if you have some strategy on subscription, that's fairly straightforward, or is this just all start?
Yeah, it depends. Sometimes it's no. We'll see what. I've been working around DOS recently. We have a bunch of.
On va y aller, c'est bon ça. Donc on a dit...
Je vais essayer de raccourcir.
Vous avez 30 normalement. Ok. Oui, normalement c'est 40 minutes, c'est 30 plus 10 ou 35 plus 5. Okay, the next presentation. The floor is yours, guys. Switch. Il y a tout switch. On va attendre quelques secondes avant qu'il s'allume en principe. Ah, ok. Il passe au vert. Test. All right. Is it okay?
No. So
No?
if I can take this one.
Test. All right. So welcome in our talk. So this is a research project, a joint work between Aurélien Hernandez, which is there, Romain Kerr, Aurélien Farcillon, and Clémentine Maurice, and myself. So the work was done during my PhD studies at Euricom, and today I'm a postdoctoral researcher at Las CNRS. And so the research project is called Phase-modulated, and basically it is about a novel way of exploiting electromagnetic side channel attacks, and more specifically, phase-modulated emanations. So let's jump right into it. So, okay, this is not working. All right. So this is exactly what we are talking about. So here we are extracting secrets from a microcontroller. So this is the target device. And basically here, there is the computer that is performing measurements through the radio receiver. The radio receiver which is connected to an IM probe, and we are measuring the magnetic field around the microcontroller. And this is leaking the secrets which are inside the microcontroller. And so basically here we are using a radio receiver. This is typically done using oscilloscopes in more traditional setups, but this one is way cheaper. And our talk here is about a new way of exploiting the emanations that are captured by the EM probe. So let me explain a quick reminder about side channels and why we have them. So basically, let's consider a computing device. It will inevitably interact with its environment in different way, and the unintentional emanations can propagate in various mediums. So for example, it can propagate into the electrical system, so you can measure it through the power consumption. It can propagate through light, through acoustic waves, or electromagnetic waves, and often in radio frequencies. And in our talk, we are interested into those ones. So basically, to perform a side channel attack, just to have a quick overview of the different steps of the attack, there is a victim that is doing the sensitive operation, and the attacker will build a dataset. So this is a dataset of traces composed of a lot of different measurements. And basically a trace is a measurement, that means an absolute measure of a physical emanation. And so for a specific set input, you will have the same measure with, of course, a random noise on top of that. So basically, the attacker will build a model that will be used to perform some correlation, and based on this, the attacker will be able to guess the secrets. And so why do we have those emanations? If you take a microcontroller here, and you consider a small difference in the logic inputs of this microcontroller, inside there is hardware, and for example, with CMOS logic gates, the static power consumption is not dominating, but the dynamic power consumption is dominating. So the power consumption of the chip will be different based on the transition between the input values. And this is why we will have a difference in the physical emanation. For example, the power consumption. Okay, so basically, our contribution in this talk is how we can exploit unintended phase modulation of the electromagnetic signal. So that means how the secret is transmitted or leaked by the microcontroller. And so in this talk, basically there is a first part where I will present how to exploit them and how it works. And there is a second part where we will investigate why we have this phenomenon. Okay, so to explain how to exploit this, I will make a small detour through how it is commonly done. So basically here, our contribution is exploiting phase-modulated emanations, and here I will present you the traditional, more traditional way of exploiting amplitude-modulated emanation. So basically it is known in the literature since more than 20 years that if you take an amplitude trace of an electromagnetic signal, it can be used just as a proxy of power traces. So you can use power correlation attack, for example, on electromagnetic measurements using an amplitude trace. So to understand this, we need to understand exactly how to compute the amplitude of measurement. So basically you have your signal here with three main parameters, the amplitude and the frequency, and we will talk about the phase later. So this is the representation that we call the real valued signal. And so basically this is what is, it corresponds to the output of an oscilloscope, of the samples of an oscilloscope. But there is another way of describing the same physical phenomenon, so an oscillating wave, but there is another mathematical representation. Basically you take the first equation, you rewrite it in a sum of a cosine and a sine, and then you write it as a complex number. There is some mathematical tricks behind, we don't care here, and basically this is called a complex valued signal, and this is also called the analytic representation. And this corresponds to the output of a software-defined radio, the kind of radio receivers that we are using. I will talk about them just after. So basically, to represent this graphically, you can do this in a unit circle on polar coordinates. So you can plot your I and Q, which corresponds to in phase and quadrature. So you can plot them just like this. And if you want to compute the amplitude, which is what is traditionally used in AM side channel, you take the magnitude of the vector, of this vector. Okay, so this is what the output, this is the representation of the output of those kind of radio transceivers. So basically, these are called software-defined radios, or SDRs, and basically they are way more cheaper compared to an oscilloscope, and those are radio transceivers that we can configure by software, hence the name. And the architecture of those radio transceivers are pretty different compared to an oscilloscope. So if you look at them, you will have a typical architecture. This is a simplified view, of course, but basically you have your signal that is coming to the antenna and an amplifier, and on the other side you will have typically a PLL that is generating a sine wave at the frequency that you want to measure. So this is the carrier signal. And this sine wave will be divided in two branches, one which is not shifted and one which is shifting, so from 90 degrees. And this is our in-phase and quadrature components, or the I and Q that I was talking about just before. So basically there is two mixers, which mix our carrier and the received signal, and they are filtered and the final ADCs. And we will have our I and Q samples, or in phase and quadrature. All right, and why are we able to measure this using those kind of hardware? Well, basically, if you look at the emanations on the right, they are transmitted like a traditional modulation in typical radio communication. So this is called an unintentional modulation. And there is many kind of modulations. And on the first modulation, you have a typical amplitude modulated emanation. And on the bottom part, you will have a phase modulated emanation. And this is exactly what we are talking about here, exploiting this new way of demodulating the signal that you measure. So basically, for an amplitude modulation, there is a message signal. So in a side channel context, this is our secret. And there is the carrier. And in the side channel context, this may be often a clock, a digital clock. And so basically, you will embed the message into the amplitude of the carrier, and you will have this beautiful modulated carrier. And you can see that this amplitude varies according to the original message. Okay, so to summarize, here we know how to represent the signal. So the real valued representation, the complex valued representation. We know how to measure it using a software-defined radio. And we know how the information is embedded inside the signal through the modulation. For example, amplitude or phase. So now we can perform the acquisition of our signal, so building the dataset, demodulating them to extract the information, and performing the side channel attack to retrieve our secret. All right, so I will describe how we do this for the amplitude. Again, this is what it was already done in the literature. So you have one sample from your SDR. So this is only one sample composing a long measurement. And you will compute the amplitude, so the magnitude of the vector. You will do this for all the samples that are composing your signal. And in the end, you will get a new trace. So this is a real valued trace, which is the amplitude function of time. All right, and if you look at it in practice, it will look like this in the time domain and in the frequency domain. And here you can see in the frequency domain 4 different AES execution, and in the time domain, we zoom on one of them, and you can see the key scheduling and the rounds. Okay, so that was what was typically done in the literature, and now I will present you what we are doing and how we are doing it using phase-modulated emanations. So basically, if you get back to this one, our work is parallel to the previous ones, and we are demonstrating how electromagnetic phase is also a proxy trace for power measurements. All right, so basically, if you take this one and you look at the phase, it corresponds to at which point the sine wave is in its period. So if you shift a bit the phase, you will get a signal shifted like this. And if you look at the complex representations, the IQs, it's the angle of the vector. So for the modulation, it will look like this. The message here is embedded in the phase of the carrier on the left, and it will produce this kind of modulation, and visually we can see that the frequency is varying depending on the value of the variations of the input message. So basically, to compute a phase trace, to use it just like amplitude in side channel attacks, there is 3 steps. The first one is computing the instantaneous phase, or the wrapped phase. Basically here, this is really analog to the amplitude computation. You take your IQ samples, you compute the angle using the argument of the complex number. You do this for all the time samples, and you will get a real valued trace. Great, but this cannot be used in this form directly into a side channel attack, because if you remember, the phase is a cyclic measure compared to the amplitude. So if you have a small variation like this, you will have a high discontinuity in your real valued trace, and this is not usable directly into a side channel attack. So this is a problem that we will solve with our second step, which consists of computing the continuous instantaneous phase, or the unwrapped phase. Basically, it would transform the first signal or trace into a cumulative function. So basically, you will add a factor each time you encounter a discontinuity, and you will have the cumulative function. So it will look like this. This is great, but still, that means that at a specific sample in the end of your signal, it will be influenced by all the previous samples, and maybe there is noise, maybe there is errors. So you don't want this behavior. So basically, we will take the phase shift, and I will explain what is a phase shift. Basically, if you look in time domain here, you have two signals, for example, an idle one and a measured one, and the phase shift will be the difference between the two in radians. And you can compute this also for the other representation using a measured sample and an idle sample, and you will look at the phase rotation. They are the same phenomenon in two different representations. So we want to compute the first derivative, which is a numerical differentiation, and we will have the phase shift between all of our samples. And basically, if you look at them, it's like this. And maybe it will remind you the previous plot. They are very similar, and that suggests that we can use them in side-channel attacks. So this is how we will exploit them now. Basically, this is this setup that we use. So this is analog to the one that I showed you at the beginning of the presentation. And we tested this on many different SOCs, system on chips. So basically, the steps here are you take your IQ samples, you compute the amplitude for the amplitude attack, you will perform your attack, for example, a CPA, correlation power analysis, and you will perform the key enumeration. This is an example of the results here for the amplitude only, and basically here the lower is the better. So as soon as the curve reaches the 0, that means the full key is recovered. So here in 300 traces. Okay, let's do this with the phase shift trace that we computed before. This is all the same steps, and we will have those results. Okay, this is better, this is great, but there are some questions that are rising now. Maybe are the two information identical or different? And if they are different, maybe they are complementary, and could we recombine them? And so the solution to this is to use multi-channels attack, that is to side-channel what diversity is to radio communications. So basically, you perform the same steps as before, but before the key enumeration, you perform a fusion or a recombination. So here by adding the different correlation coefficients. And at the end, you perform the key enumeration. And by doing this, we have even better results. And if you look at the point at which we retrieve the full key, it's twice traces than the first original attack. And if you look at the middle of the plot, at 150 traces, it is orders of magnitude better than the original amplitude attack by using both of them. So that's how we exploit the phase-modulated emanations, and that's how they perform. And now we can dig into the root cause analysis of this phenomenon.
Thank you, Pierre. Okay, so now we have like a new way of exploiting side channel using phase electromagnetic modulation. But there was some question behind it, like what was the correlation between the phase we externally observe and the CPU consumption? That's what we try to understand there. So that's the second step. So first we try to emit some hypotheses. Let's take back the big picture. So we have the classical electromagnetic amplitude that has been exploited quite some time ago to proxy the power consumption. Recently, we have the EM phase with part of the work done here. But the link between EM phase and power was still unknown. Something is missing, and we had no understanding of the path between the two. So we dig a bit in the literature and also in the electronic engineering field. And we discovered that in between, there are researchers that managed to exploit something that is called jitter. So jitter is a simple concept. Basically, it's analogous to the phase, like we've seen before. But like instead of measuring the phase shift in radians, the measurement, instead we do it in seconds. More generally, we use a jitter when it comes to digital signals. So with microcontroller digital signals, we more commonly use the jitter as a measure of phase, let's say. So those two publications, they exploited the jitter, they observe it in order to retrieve the power consumption and build a model on this. So first, in 2021, they managed to exploit this by a purely software means by reading the coefficient, the correction coefficient embedded with a high-speed data bus, such as DDR for RAM. It can also be USB 3, for instance. There are those high speed, because they use delay lines to correct, let's say, the timing on those digital bus, and they are really prone to jitter, and they manage to correlate it with power consumption. More recently, in 2023, we have also a purely external jitter measurement with measuring equipment, and they managed to retrieve cryptographic keys from a cryptographic implementation. So that's interesting. Let's see if there is a link between the phase we managed to exploit and this jitter effect on a microcontroller. So if we take a closer look at the internal of a microcontroller or a system on chip, a more complex one, we can see two interesting things. Like we have two noise-sensitive components that are prone to generate jitter on the clock lines, which are the clock generation circuit. So it's a big picture, but clock generation circuit can be quite complex on microcontrollers and are really prone to generate jitter because of noise. And then we have also the clock tree, which, like, the main goal is to propagate clocks all across the chip in order to have a perfect timely arrival of a clock at the different place of the silicon die. So it can be the CPU and other digital component inside. So those two are the sensitive one, and then we have the CPU. All of those are connected together to a power rail. Thanks. All of those are connected together on the power rail, and of course the CPU nearby is like getting a variable amount of current in time, and this can generate noise, of course, if they are connected to the same power rail, like for instance to the clock tree. And this is one of the hypotheses that has been quite explained before in the literature, but we also wanted to extend it to the clock generation circuit, because we know from the literature it's really a sensitive component. It's worth to know that in some implementation, for, like, of course, for engineering issue, they have to decorrelate the power supply of the clock generation circuit and the rest of the digital design, so sometimes it may not apply. So this is what we call the direct coupling path, but then we may find some indirect one that we call on-chip coupling. Those are parasitic coupling that happens with inductive effect or capacitive effect, for instance, that can impact from the CPU activity to the other sensitive component through this coupling. So this is what we call the indirect path. The issue we have here is that if we wanted to confirm those hypotheses, the issue is that, like, CPU and microcontroller are really complex, really small. So inserting probe, for instance, electronic probe to get some measurement internally is really costly. Also, there are broad amount of different implementation of a system on chip. So this is we have also the diversity of the design. And yeah, also if we want to do it fully by simulation, the complexity is exponential. So we had to take a bit of a different approach by trying to empirically find a correlation, verify it, let's say. So we move on to the experiment we did. Let's take one target. So in order to do those empirical things, we had to take one specific target, which is the STM32F. I guess it's a well-known microcontroller, general purpose one. It was really interesting because it allowed for high flexibility in the clocking circuit, so this complex internal circuit that create and generate different clocks. We had a lot of control on its configuration to enable or disable specific components inside of it, and also the observability. We had this feature to conveniently extract one of the internal clock out of the CPU, so an internal one, for further jitter measurement. So we hook up the target microcontroller with a high-speed oscilloscope. This one is from the Siglent brand. Anyway, high-speed one, I guess it was 4 gigahertz, something like this. We retrieve all the traces, the jitter, like the measurement traces, and then we perform the jitter measurement on a laptop. But at the same time, the laptop is providing different configuration to the target. Those configurations are used to create different type of power consumption profile. Let's say, depending on which type of firmware you will run, this will exhibit a different power profile. So we try to create simple ones, as a simple example, So we have the sleep state, where we completely shut down the CPU. The rest of the IC is still powered on, but the CPU is clock gated. Then we have the stall state configuration, which is simply an infinite loop, so we just branch over and over. There is no specific computation, no floating point whatsoever. And then we have the AES, where we reuse the same tiny AES implementation, and we continuously compute blocks. So the last one, of course, should exhibit the highest power profile among them. Then we try to even create more overconsumption events. So we had this idea of connecting the target with something that is called a chip whisperer. So basically it's a platform for side channel, and we reused one of its capability to perform a short circuit, really fast one at precise timing. So basically we just short circuit a GPIO, for instance, that is active high. This should create even more overconsumption so that we can measure the jitter later on. Lately, we also reused the external signal generator because for our experiment, we needed a really stable reference clock, let's say, to be used as a reference one. So the first result with the different CPU profile, CPU configuration, let's say. So here is one of our results. So the red line is our baseline, so the nominal clock of the CPU in nanoseconds. Then we have the different CPU configuration. So we got some results. So for now, without any short circuit even, we can see that depending if we're on sleep, stall, or AES, we get increasing amount of jitter noise, let's say. So we have the mean value, then the inner part, which is the standard deviation, and then the outer part, which is the maximum and minimum value. And yeah, we can see this difference, and which is even more noticeable when we enable the clock glitching circuit. So we call it a falling edge because it's the moment we start glitching. So we put the GPIO at, we force it to 0, which creates the short circuit. And we can see that all of the mean value gets lowered, and the standard deviation gets even increased. Which is, like we get a way higher jitter at the moment we start the glitching. The same applies for when we have a rising edge, but this time in the other direction. So we increase it temporarily, the clock frequency by jitter. So this is for the power consumption comparison. Then we also did some experiment really quickly with this internal clocking circuit. We can see that depending on the configuration, because we can provide it an internal or external clock, we can use inside a PLL, which allows to multiply the clock internally to run the CPU at higher speed. And we can see, and this PLL, phase lock loop, it's also really sensible to noise, surrounding noise. And yeah, we can see this comparison when depending on which component we enable inside, the more sensitive component we have enabled it, the more jitter we are prone to obtain. And finally, we also did our short circuit experiment with on top the SDR receiver measuring the phase in the electromagnetic emanation of the chip. We reuse the same setup as before. And basically, we can observe that when, at the moment we start the glitch, we can see that we have a transient phase rotation in one direction, and the same apply when we release the short circuit. We have a shift in the opposite direction. So overall, for those results, so yeah, this is pretty preliminary. We have to treat it with precaution, and especially because of the complexity of understanding what are the underlying effects on the chip. There are also a bit of consensus around this, but really a small amount of publication yet. So those are early results, but still promising results because it shows like an interesting link with CPU internal component. So the overall conclusion to this talk, to summarize the targets, so we managed to exploit 4 targets. All of those, you found them in a lot of IoT devices and components. Those are really well known. The only one that we didn't manage to exploit is the Raspberry Pi 2040, which is a microcontroller from the same company. I think it's interesting because in both the traditional amplitude and amplitude, we didn't manage to exploit it. I guess this part is also ongoing research, why in this case we don't get interesting results, despite it's kind of a simple microcontroller, let's say. So overall, I think the EM phase, it's like a good addition in the side channel research field, a good addition. We can see that from a higher level point of view, it's really interesting to see the interaction, like from the software designer point of view, the interaction between the software and the surrounding hardware. And also, we get it from a lower level point of view, because it's really interesting to see that all of those physical phenomena are exploitable below the functionality threshold of the designer. By this, I mean that a lot of engineers and designers design their chip in the way that ensure its proper functionality for some specification. But all of those attacks, let's say, they manage to exploit something below the functionality threshold. And that's really interesting to see, depending on which side, which abstraction level you put yourself. So overall, we had some future idea and let's say overall future work. So the idea would be to better statistically prove the correlation, and that amplitude and phase are actually different and complementary effects. Those are not linked in some ways. So we have to continue toward this and show that this is a different phenomenon. Also, we also want to assess something that is interesting is that software-defined radios are really cheap. You have entry-level one that really cost $20 at most. And it's interesting to see how they compare with traditional oscilloscope samplers, hardware that are usually used in side channel attacks, and how they compare together. I think it's an interesting comparison. Overall, the application of this new attack is quite interesting because, yeah, maybe like for targets that side channel attack was not considered a threat, like trusted execution environment, secure element, maybe in this case, and this has to be assessed, the phase leakage that you get out of it might be threatening now in this case. Also, a system not vulnerable to EM amplitude might, in this case, be exploitable in phase. So that's the end of this talk. Thank you. So again, this research has been published at the Chess Journal in 2024 and will be presented at the Chess Conference in 2025, September 2025. I guess we have a bit of time for questions. Again, if you have still a question afterward, don't hesitate to contact us. All the artifacts, the slide deck with all the reference and citation we used are available. And don't hesitate to check it out if you're interested. Overall, I hope that this raised a bit the interest towards side channel, at least in a good way. Thank you.
Thank you. Thank you.
Do we have questions? Yes, over here.
Okay.
Hello. Thank you for the talk. I was wondering, so you are presenting something new to me regarding side channel. How does it behave when the application software is like masked, because masking is the most present countermeasure against side channel?
Yeah, so how does it compare with masking and other countermeasures? So we don't have any experimental answer because we didn't do the experiments. But from what we observed, at least when we had a leakage on the amplitude, we always had a leakage on the phase 2. And when it was not the case on amplitude, it was also not the case on the phase. So what I would hypothesize is that if with the countermeasures like masking and so on, you have a leakage on the amplitude, it will probably be the same on the phase. And if it is not, for the amplitude, it will not be on the phase. This is our hypothesis, but this is still a future work for cryptographic countermeasures.
Question, sorry, there is another, just before you.
So about the software-defined radios, it seems that you set a frequency for the measurement. If I understood correctly, the scheme, say you have a reference frequency, and how do you define it for the attack? Does it have some impact on the results as well?
Yeah, so for the frequencies of the measurements, they changed for every system on chips. But basically, we always did that either at the clock frequency, its main system clock, or an harmonic of the clock, because it is well known and it is easy to observe that there is very often a coupling between the leakage and the clock signals in our system on chips. And so you can find the modulated leakage on the clock emanations or its harmonics. And one interesting fact that we developed in another paper is that there is always a main system clock in the system on chips, but there is also a lot of sub-clocks that are used for special parts of the system on chips. So for example, you will have one clock to 64, another one at 32, and other frequencies. And you may be able to find the leakage on all those clocks frequency and all those harmonics. And since there is a lot of harmonics and a lot of clocks that are coupled with the secret, that means that you can sometimes find the leakage, for example, from 50 megahertz to 30 megahertz. And for all of those frequencies, you may be able to find, not in a continuous way, but in sporadic ways, but at multiple times, you may be able to find the leakage. So if you want to see the precise frequency, they are all in the paper. But basically, this is targeting clock frequencies.
Okay, thanks a lot.
Okay, last question. You make the hypothesis that amplitude modulation, amplitude and phases are not correlated. But what if they are correlated and that the effect you see is caused by just an additive effect on the information you get that allows you to go to the result twice as fast as just with one part of the information. Alors je vais la faire en français peut-être sinon.
As you want. I think I got it. So for you, it's like the assumption is that the amplitude can be the phase can be a side effect of the amplitude, and actually we thought about it because like maybe it's just a matter of signal processing, and probably we observe the same thing in a different way. If I'm correct, like in some case that we try to isolate both, and that's why we did also this experiment with hypothesis on the clocking circuits. And like also taking all of the knowledge with the exploitation of soul jitter, and with jitter exploitation on digital line, you don't have amplitude information in it. That's still an ongoing question. I mean, in some cases, we managed to observe a strong phase modulation on some frequencies, while on some others, on amplitude, it was a bit lower. So this was a hint. Okay, in some cases, and also depending on the frequency. Sometimes we try to observe like frequency for system on chip, like at the Wi-Fi frequency. We try to observe like if there was some phase shift due to the internal transceiver, and it was only modulation. So yeah, it's hard. Maybe in some case you have both that comes from one phenomenon. In some case there are the two separate things. Maybe also in all the amplitude side channel literature, they were also exploiting a side effect of jitter and phase. Yeah, that's the tough part. How to isolate them, and I guess it's a case-by-case basis. Still, we have enough hint in some case, a lot of cases, those two are adjacent, let's say.
Okay, thank you. You have to stop now. We are late. So thank you. Thanks a lot.
Thank you.
So we are now 20-minute breaks. Yeah, we have said that. Okay, be careful. If Antoine and Anthony are here, can we check your presentation, please? C'est bon, c'est ça? Ok, merci, c'est good. Merci. Alors, il y a une autre présentation.
are still empty. So if you want to have fun hacking into some IoT devices, then you can register on the THCon website. There is a submenu where you can, I think it's to reply to a poll, like probably a Google something, okay? I don't know those names. Yeah, so please,
Okay.
Vincent, proceed.
So thanks you, everybody here. We switch to the next presentation from Antonin Verdier from IRIT. The title of this presentation is a new dataset for in-depth understanding and inconspicuous software.
All right, everyone can hear me? Hello everyone, I'm Antonin, thank you for having me, and I'm going to talk about living off the land attacks and our dataset and associated taxonomy for detecting them. First, a little bit about me. I'm in my third year and hopefully last year of my PhD thesis working on defense against low footprint attacks. These englobes DLL search order hijacking attacks that I presented here 2 years ago, as well as living off the land attacks, which I'm going to talk about in detail today. Regarding my hobbies and various shenanigans, I have a lot. I'm not sure if it's normal that nothing's displayed there. I mean, it's not the most important part, but still.
Could you switch what's projected on the screen? We need the slides, please.
Yeah. Oh, thank you.
Thank you.
This is fine. I'm just going to skip over that. It's not as important as the rest. I would like to start by presenting you with these two command lines. I don't know if they're big enough for everyone to see. They're just two tar command lines. And I would like to generally ask you what you think they're doing. The first answer is, it's all right, tar can't handle remote files, so the first command would fail. Second answer is some backups are unloaded with their execution permission stripped. Here comes the train, and for everyone who has to look up options every time you want to use tar, something archives. So rapidly, who thinks it's answer A? All right, answer B? C? Yeah, answer D. Right. The video should show you the answer. So the two commands are going to be typed one after the other. So this is already a bit weird for tar, but I think the second command will surprise you. Yeah, that's not usual behavior for tar. And this is not usual behavior for ls. So let's delve a bit into what these two commands actually do. The first one starts in a way that you might have seen before, tar xf. We want to extract an archive. The subtitles are a bit messed up. It's not supposed to include root. We then want to extract a remote archive, and the remote server that contains the archive is accessed through SSH. So far, we are using tar to download a file and extract the archive we just downloaded. In second time, this command will also extract an archive, tools.tar, which was contained in the backup.tar archive, but with a little twist, because tar is instructed to execute a command whenever the command /forbidden, which is an executable that was dropped from the backup.tar archive, whenever the first record, so the first block of data inside of the backup.tar archive has been processed, effectively executing something we just downloaded from a remote server. We might think that the obvious solution to this is just to blacklist the combination of parameters that we just use and try to categorize them as malicious through ways of command line signatures akin to standard antivirus methods. But this does not really work in reality. The first reason is there might be actually a benign use for these commands. People might use those without any malicious intent. The other reason is you can do that with tar, but you could use tools such as wget and just calling the script after giving execution permissions. Or you could use SCP, which always give the permission that were on the original file and just call the script. You could also mix them up together. So as you can see, just trying to block specific commands does not work because we can use a variety of different combinations of software components to obtain these malicious behaviors. And there is a very obvious overlap between legitimate and malicious commands. For example, it's highly unlikely every wget command you will get executed to download a file on your systems is going to be malicious. So you can't just outright block wget. So based on that, the succession of command I presented is an example of living off-the-land attack. The basic principle is to abuse the functionality of legitimate software components, such as star, wget, or SCP, to perform malicious actions. This is often camouflaged by a lack of knowledge from system administrators as to the actual capabilities of what the software components they trust and are sometimes pre-installed can do. The motivation is quite obvious. Using these techniques, threat actors such as APTs can hide in plain sight, avoiding, for example, the scrutiny of introducing foreign binary files such as Mimikatz, for example. Also, in very strict systems with strict allow lists of executables, if you can just abuse the possible behavior of a software component that is trusted, that is part of the allow list, you could still end up infecting and performing malicious behavior on your target platform, even though technically nothing can enter the platform. I'm going to go briefly over this to try to stay in the timing. This is a basic review of literature. First off, there are knowledge bases such as LOLBAS and GTFO-beans. We try to basically record every possible manipulation of default installed software on Windows and Linux. Sometimes they will associate, yeah, this is really hard to read, I'm sorry. They will show examples of attacks you can do with software components and provide detection rules for those attacks, which, as we discussed earlier, is not really a viable approach. Researchers also proposed using machine learning models to detect such abuses. Stamp and colleagues proposed a solution that basically involved training one detection model per specific software component we want to have detection capabilities on. I think my PhD supervisor a few days ago tried to look at the amount of software components installed by default on Debian Linux, and it's around 1,500. So this is not really feasible in real life. Other researchers propose active learning approaches, which do not necessitate big, malicious and benign sample datasets in the beginning. This is quite interesting because it has an ability to evolve over time, but still requires human interaction and human expertise as time goes on and new attacks are created and discovered. Another interesting approach is to look at the command lines that are being executed. Basically in the same way that a detective or just a human analyst would, trying to look for certain keywords or certain elements such as public IPs, and basically constructing a feature vector for machine learning. That's a selection of flags based on whether or not certain words or certain regular expression match its contents. This is interesting because of the approach, but in the end, this is what we call a bag of words approach in natural language processing, which is quite limited by the fact that it lacks context. Yes, we are saying to the machine learning model that there is the command bash, there is netscat that's being used, there is an IP, but there's no information about how those different elements are combined together. There's no information about the pipes being used and so on and so on. Another interesting approach is to try to detect suspicious communities of processes. The example on the right is a process graph where parent processes and their children are represented as nodes and connected through edges. The idea is, in addition to all techniques regarding the understanding of the command lines being used, we also look at the prevalence, at how rare the different parent-to-child relationships happen. For example, it will be quite common if Chrome is started by Explorer.exe, just the user clicking on the browser to open it, but if at some point Firefox spawns a PowerShell process, this is a bit more suspicious. As such, such a rare occurrence of a parent-to-child relationship will be marked with a heavier weight on the edges connecting nodes on the process graph. This is interesting from a graph perspective because we can use community detection algorithms to try to isolate parts of the graph that have, a lot of these suspicious relationships grouped in a small amount of space. Finally, the last contribution I wanted to mention is that of Holmes, where instead of looking at the specific programs that are being called, they instead look at the system calls those processes make in time and try to map the various system calls to TTPs from the meter attack matrix and try to map those to APT stages from the APT kill chain. This is a very interesting approach because it completely decouples the detection from the underlying software, which, as we've seen earlier, can be basically combined, swapped at will to make these attacks. However, it suffers from a few weaknesses in the way they are mapping the system calls to those TTPs, which are basically based on some assumptions that do not always hold. We can talk about those later if you want. I don't think it's as important right now. So now that we've identified that basing our detection methods on strictly the commands being used is not efficient, what can we do? Well, if you remember earlier, I said that SAR was basically used to download the remote file and to execute what was downloaded. What we propose is instead looking at the actual behaviors of the command. Every one of the combinations and swaps of commands I proposed was still executing in the end the following operations: downloading the file, setting permissions for execution, and then executing the file. If you want to be more in details, we could separate downloading the file as network communication resulting in the writing of a file. As such, our goals were to create an initial dataset that would reference and map commands, command line program commands and their options to a list of behaviors, basically allowing to map a whole manual of command line program to all the behaviors the program could exhibit when all their options were being used, basically mapping certain options, for example, the -O on curl to a file writing behavior. We aimed for the dataset to be representative of Unix-like CLI software, so basically to have a bit of system utilities, to have some file downloading utilities, just regular network utilities, archive management utilities, and so on and so on. For this dataset to actually be useful, we also needed a taxonomy of behaviors, basically a list of different behaviors that are distinct from each other with a consistent level of abstraction. We don't want to categorize an option as being file reading and another as being compiling a program. We want to keep the level of abstraction consistent so as to be able to combine those behaviors together in a way that makes sense when we look at basically behavior graph or graphs of behaviors interacting with one another. This posed a few challenges. The first one was finding the reasonable abstraction level that I was talking about, because we want to be completely decoupled from the underlying software, but also we need behaviors that can be chained and combined, such as network communications, file writing, file reading, and so on. Regarding the datasets, the challenges that we encountered while trying to find a taxonomy meant we had to frequently relabel the whole dataset, which is now around 880 samples, I think, so you can imagine this takes quite a bit of time. And sometimes we had to spend extensive time testing different options because the manual can lie sometimes and not actually describe what the option is doing. It was also a bit hard to simply extract the documentation of samples from the manual because there is not quite a standard way to write a manual, even with the man command on Linux, so this was another challenge. Regular expressions sometimes just couldn't cut it. And finally, there were some options that are, let's say, less than ideal for machine learning applications. Basically, if you've got an option that says, hey, I do the same thing as this option, but in this context, well, by default, this doesn't give us much information to give an appropriate label to the option. In the end, we've got an 880 samples dataset, so this means across 23 different software programs, we labeled every option of these programs, and sometimes the programs, mapping each sample to one or more behaviors. So we've got 11 distinct behavior classes, basically command execution, file handling, file stream handling, network communications, information gathering, and then operations on the file system. And argfile is a bit hard to explain, but it's better explained in the paper. And finally, we've got the neutral category, which is a bit apart, meaning using such an option won't introduce any more interesting behavior, at least from a security standpoint. This is an example of 3 records from our dataset. The first one being about the SFTP command itself, which is mapped, its inherent behavior would be network communication. This is what SFTP is designed for. However, we cannot imply that using SFTP will result in either file reading or file writing, because you might use it for one reason or another. To illustrate the case which I talked about for having more than one behavior associated with an option, there's the -p option, which is to preserve basically an amount of metadata whenever you're uploading or downloading a file. This means when you are downloading a file, you will have to modify the metadata on the file system, which is related to file system operation. And when you are uploading a file, you will have to query the metadata of the file you're uploading to be able to preserve it, which means file system information. Earlier, I mentioned having jumping abstraction levels, which is the case of the LOLBAS and GTFO beans knowledge bases. This is better illustrated here because in some cases we have pretty good one-to-one correspondence between our behavior taxonomy and that of the other knowledge bases. This is the case for example, the copy behavior. But in some cases, for example, on the second line, LOLBAS will be much more specific about file reading and file writing, categorizing it as jumping, obtaining credentials. This is very different from just the encode operation they were describing earlier in terms of abstraction level. As you can, I'm not going to go into detail for every line here because I don't believe it serves that much purpose. I was just trying to illustrate how much the abstraction levels are all over the place and not really useful in terms of chaining those behaviors together as much as detecting specific actions that you could interpret as being malicious or not. In some cases, there are also behaviors that they call functions that do not even really correspond to one another. For example, compile, temper, or conceal in the case of LOLBAS, which is even weirder because I think at least one of them has only one command associated to them, which basically means they created a category for that specific sample, which is a bit weird. We also considered using machine learning approaches to expand the dataset. So as I was saying, we had to have multiple iterations of the dataset labeling process, which took a lot of time, and we wanted to see if we could basically enroll an AI agent. I'm using the agent term liberally. I'm not necessarily talking about large language models here. Basically, having an AI component that will help us label the dataset, help us label new programs by basically predicting the behavior class for a given option. We compared a lot of approaches regarding feature extraction or actual machine learning algorithms. We considered having one single model that could give the class of the sample that was provided versus using a one versus rest approach and multi-class. Rapidly, this is the approach that yielded better results, OVR plus multi-class. In the first step, we will just get feature vectors from sentence embeddings, which is what we found yields the best results. And in the second stage, the sample will first go through a one versus rest classifier, which will basically tell if that sample is supposed to be neutral or is something else. And if it's something else, it will go through the multi-class classifier, finally giving it its actual class, behavior class. For all of these approaches, we tried with and without data augmentation, basically creating new sample, which is quite easy theoretically when you're using sentence embeddings. And we considered hyperparameter optimization for every one of these approaches. For example, modifying the learning rates, the amount of trees in a random forest, and and so on and so on. Overall, we train over 500,000 different models to try to get the best combination of hyperparameters, and I guess I would call them hyperparameters, but the choosing of algorithms and the method for feature extraction. Overall, we found that it's unfortunately not that reliable. Those are the results for the detection of, it's the one versus rests models basically determining if something is neutral or not, which is about okay, but it really goes down when we're trying to actually give out the correct class. This is partially explained by our dataset being relatively small for such algorithms, and on the other side, this model is responsible for assigning a class across 10 different classes, which is kind of pushing it regarding the size of our dataset, sorry. However, even though this proves that we can't, at the moment, use machine learning approaches to fully automate the expansion of the dataset, it can still be useful in the labeling process. We would basically, one after the other, review each sample and assign one or more categories. Well, with such algorithms, we could have basically the machine learning models make a best effort to try to, by default, select the correct the behavior it thinks is correct for the sample, which would in the end still be a gain of time for us when we are expanding the dataset. We also recently considered using large language models and fine-tuning them for this purpose. The initial results were better, but it's hard to properly evaluate because you need a lot of computing resources to make this fine-tuning happen. We tried a bit of in-house fine-tuning with the processing clusters at my laboratory, but didn't really get good results. And we tried to do a bit of cloud-based fine-tuning on Google Gemini and Mistral Large, the latter having the best results. Unfortunately, we couldn't do many dataset splits to prove how efficient it is, so we're not entirely sure at the moment how good it is in actuality, and we need to further research that perspective. In the end, we, however, obtain a dataset with a good variety of software types. We've got curl in it, we've got a part of OpenSSL, we've got tar, we've got LS listed, and many more. As I said, I think it's a bit more than 10 different software programs. And the dataset is completely open source. It's available on GitHub. There's, I think, a link on the last slide, but you can talk to me about it. Or just if you type, did you misbehave on Google, it's one of the first results, I believe. Our dataset and the labeling we did for it is anchored in tests and rigorous study. As I mentioned, we had to spend a lot of time actually testing if the description the software manual did of certain options was actually close to reality, if it was actually describing what was happening, or just describing a small part and kind of ignoring some side effects of using these options, which was kind of hard when it came to labeling, because we had to consider whether to label what was written in the manual or what the option was actually, what behavior the option was actually exhibiting. We believe our taxonomy is adequate because we've been able to label correctly most of the samples we have encountered in the labeling process. However, it is not exactly perfect. Some samples do not really correspond to any of the behavior classes we determined, and there is a clear class imbalance across the dataset. For example, neutral samples represent about half of the dataset, which can be another barrier to having good performance with machine learning models. And yeah, as I mentioned in the previous slide, we need to further investigate the use cases of large language models to aid or even hopefully automate the dataset expansion process. And this used to be the future work slide, but this is current work. This is what we're currently working on. The next idea is to use this dataset, this knowledge base, and the taxonomy to basically translate process graphs. In the left slide, if the graph is too hard to read, there is also a text representation. We are basically splitting command lines into their various parts, into their options, and then from the knowledge base, applying the information we've got on each option and program behavior, which would look something like this. The implication being that if we were to swap and combine different programs, as I showed in the beginning, we would still get very similar looking behavior graphs in the end on which we could actually perform detection of potentially malicious behavior. Thank you for your attention. Have you got any questions?
Thank you. Do you have any question? Yes. Fais du sport.
First of all, thank you very much for this beautiful speech. I found the GitHub, but it's empty. Will you soon update it with the dataset, or maybe just your database of command lines so we can just check in when we are doing detection?
Currently, the GitHub repository does have the CSV file of the dataset, but yeah, at the moment, I'm going to include the paper and probably a better description of all the behavior classes, which I understand is lacking. But yes, I plan to enrich basically the GitHub repository to make the dataset in its current state more understandable without necessarily having to read the paper. That would be optimal, yeah.
Okay, thank you.
No other questions?
Yeah, it seems.
I have one question, actually.
Yeah.
Oh, okay.
Yeah, so you mentioned that you got problems, you encountered problems like trying to match the actual behavior of a program with the manual. So how did you proceed? I'm curious to know.
So this was a while ago. I remember the problem, not necessarily the solutions we used. I believe when there was too much disparity between the described behavior and the actual behavior, we chose to put the sample away, which was kind of a part of our taxonomy, not being able to describe everything, I believe. But yes, some samples just did not fit into with the way we were proceeding. I believe we tried multiple. I know we tried doing both related to the machine learning algorithms, and probably for the machine learning algorithms excluded those samples because they would be too hard for the machine learning algorithms to actually learn anything from. I'm pretty sure we excluded those samples from the final version of the datasets. If you look on the GitHub repo, there are two versions of the CSV. One that I think is cleaned or something that contains a bit less samples, but samples for which we are sure of the behavior classes we're assigned to. Does that answer your question?
Yes. You want to say yes, but the microphone doesn't work.
Another question? Maybe?
Okay.
Yeah, I think that's
it.
You can just ask me later. I'm going to be here at least for today and probably a bit of tomorrow as well.
Okay.
Thank you.
Thank you
so much.
So we have a last presentation for this morning on a very different topic. Anthony, because we are going to talk about manipulation techniques in social engineering. So the vulnerability is the human in this presentation.
Yeah, so before we get started, somebody just lost his transplantation title. So he's missing anything in this pocket right now. It's a carte pastel, okay? So, and the name on it is, yeah, just check. I don't know if you can tell the name. You know, people are going to get angry, I don't know. Yeah, so if anybody misses a card, I'm going to be there, okay? Thank you.
Tu le vois. Tu prends le micro. Okay. Anthony, the floor is yours.
Hello, my name is Anthony, and I'm doing my PhD at the last CNRS with Vincent, Guillaume, and Pascal. And today I will talk about social engineering. So my background, I've studied cybersecurity and also social psychology. That's why I will talk about this topic today. I will begin my speech with 3 small stories. The first one is the hack of a search engine in 2013, which suffered from data leaks. The second one is the hack, also a data leak from a party politique the day just before the election. And the third one is money loss from a central bank in 2017. The common point between all these hacks is the entry point of the attackers. And if we try to find it, the entry point in the information system, we don't find it in any layer of the information system. And that's because the hacker targets the highest possible layer, the human layer, the user itself. And why they are doing it? It's because it's effective with 23% of success rate. And what we try to do with Vincent and Guillaume and Pascal is to understand why it's so effective. And the reason behind that, we dig into cybersecurity literature and we found almost nothing. And it's normal because it's not a cybersecurity question, it's a cognitive science question. And that's why we first make a theoretical analysis. And during this theoretical analysis, we dig into social psychology literature, cognitive psychology literature, and marketing research to find all manipulation techniques that can be used by the attackers. And these techniques can be viewed as exploits when you use a metasploit, and that's the same kind of attack. It's I will maybe give you an example. You see the foot in the door somewhere. It's a manipulation technique. When first you be asked to sign a petition, you will sign it, and then you will be asked for money. And the reason behind that, it's because you're committed into the acceptance of the request. And so once we've done this, we then asked ourselves, okay, the empirical analysis is done, but what about the real usage? So we made a theoretical, but we made then after an empirical analysis. So to make this empirical analysis, we first retrieve a huge amount of mail from a French organization named Signal Spam, which provides us with thousands of mails, and we then analyze them to labelize if each manipulation technique is present in mail or not. But for the fun fact, when we first did this, we discovered a very weird pattern. The presence a huge amount of text talking about orange and about lemon. So we first thought it was a bug, but instead we discovered that most of the mail were obfuscated. It means that the attackers will use a specific technique to make 2 different semantics. One semantics will be viewed by the user, click here to send me money, for example, and one semantic will be viewed by the anti-spam filters and all automated processing. How they are doing it? There are multiple techniques, but one of them is to put at the end of the mail huge chunk of Wikipedia page pasted in white on white, and an AI-based filter will read the mail first, but then will read the Wikipedia page, and it's like an adversarial attack. So it will classify the mail as legit, and that's how they get through the spam filters. So we made a data processing pipeline to reverse each of these techniques to retrieve the true semantics that the user see. Once it was done, we then labelized all the mail with an interface like this. We use Label Studio to do it. So for each mail, you have a check mark to check if the technique is present or not. And once it was done, here is the result. We'll not go on all the manipulation techniques. We'll only go to the top 5 most used. At the number 5, we got the time pressure method, and the name is pretty explicit, so I will not explain it. I will rather tell you how this works. At a cognitive level, in cognitive science, we got a model to describe how the cognition reacts to a persuasion attempt. And the cognition has 2 ways of process an information or requests. The first one is the heuristic method, which rely on heuristic, which are fast cue about a topic and information. For example, if you see a news on le site lemonde.fr, you will know that it has a high chance of being serious. But if you see it on PhD students are well paid, you will know it's a fake news because that's not a trustworthy source. And that's exactly what heuristic processing is. And the time pressure will inhibit the systematic processing to enforce an heuristic processing. And that's benefit for the attackers because it can fake some cues. At number 4, we got the presence of contact data, and it's rely on this heuristic I just said before, and an heuristic way. How is when there is a contact data, the source is most trustworthy. It's like the presence of the small green lock on top and left back in 2010 year, where it was known that where a website have this green lock, it means it's secure. Well, now we know that everyone can craft a Let's Encrypt certificate, but it's still an heuristic. And about the number 3, it is suspense. The ask for small things. So it's another manipulation method when we will only ask for a small request, which is not what the attacker really wants, but it will have a greater chance of being accepted. And you got some example at the left. And just before, I told you we also made our research on marketing. And behind the red line of social engineering, if we go into marketing, we got a real example of all these manipulation, persuasion tactics are used by brands, and they will ask, they will emphasize on the fact that it's really quick and it's a really simple action. At number 2, we got a semantic attack. So there, it's just usurpation of identity. It's not really a psychological manipulation method. And at number 1, we got debating, and it's very old, but very present. It's just you will you will promise for money, or the most common form that we see on our dataset is the Melanie 27, want you for tonight, with a huge amount of mail using this. If we cross the red line of social engineering, we got this technique used by brand with money appeal. Okay, so that was for the manipulation method used, and we also, with Vincent, Guillaume, and Pascal, working on persuasion through LLM, but I will go quick on it because I think we're all hungry. So we fine-tune basically a large language model to increase the persuasivity of a target, and you see an example right here. So if you try to ask it to to a commercial or open source model, it will either do not very persuasive statements, or worst, it will even refuse to comply to the request. So what we've done, we take an open source model and then we align it. We break the alignment layer, the last phase of training, the reinforcement training, and we refine tune it with complotism data to make the LLM comply with all the requests. And after, we apply two other SFT training and then DPO training to maximize the persuasivity. And you see, so that everyone know that the Earth is round. But if for someone who is already convinced that the Earth is flat, that will comfort him in his idea. And we are doing it to after fine-tuning it on phishing mails to make more persuasive phishing mails, to use more manipulation techniques that you've seen just before. And that's it. Thank you for your attention.
Thank you. Thank you for your slide in English. You have a question?
I'm looking for somebody in particular who worked in this area. Where are you, lad?
Lad? Do you have a question? No, lad, no question.
Yeah, just one question out of the blue. Yeah, I'm over here. Yeah, I'm curious about the spam dataset that you did use to train your fine-tune LLM. So where did you procure it and how? Yeah, thank you.
So the spam and the phishing datasets used for are not used to fine-tune any LLM. For fine-tuning the LLM, we used publicly available datasets in Hugging Face, where there is a pair of statements and their persuasivity score. And the persuasivity score is the measure that I will ask you, what do you think from 1 to 10 about this weather? And then I will tell you something about it, and I will re-ask you the question, and the delta between the two is the persuasivity.
Okay, thank you. No other questions.
That was a question.
So, do you think that AI is able to find new techniques, new content? Because, well, if you're a little bit interested in that, you see a huge evolution in techniques, and humans are really good to improve persuasion and so what do you try to achieve with the AI sequence? You said to improve persuasion, but do you really think that AI is able to find new techniques?
No, obviously the AI will just spit out what it's already in the training sets. But during our experiments, after the fine-tuning, we see the huge use of some manipulation techniques like the authority appeal, the obscurantism, like use a complex word for almost nothing. So it's the right combination that we will have after fine-tuning the LLM, but not any new.
Hello, thank you for your talk. You talk about AI-based spam filters in your conference. Is it possible, like, to create some kind of a sentiment analysis-based AI to detect some, like, phishing intention in a mail? Because obviously, if the Wikipedia page is not flagged in an AI-based filter, I guess it's not this working.
The filters at the moment most of the academic filters are trained on the semantics of the mail, I mean the text, and they are not trained on all the obfuscation methods. But we're currently working on a paper to automate the obfuscation methods, and so to do this, we labelize few hundred of mail to collect all the obfuscation techniques used and to develop not AI which detect this, but it can be done through very simple heuristics. Like for the white text, you can identify a CSS rule, color white, background white. For another method used is putting a blank mail and text in image. So the text is drawn in an image, and so the content of the mail is empty. And there is also heuristics for this.
I have a question. You made a mapping between the spam techniques used to lure the user on marketing ones. Have you done the other way, trying to look at marketing tricks that are not yet used by spammers?
In reality, the other way is far less used than from social engineering to marketing, because marketing have ethical limitation. For example, the semantic attack, it's not a brand cannot use that because it can't usurpate another brand, and all the manipulation methods are used by the attackers, at sometimes not used by the brand, but the marketing are very often used by social engineering.
My question is there any legal marketing ethical way of working that is not yet used for by attackers? I understand that, of course, attackers will have more tools.
Yeah, because there are because the marketing can make a marketing campaign which will be viewed multiple times, and so they allow them to, for example, to repeat a message more and more and more to make you memorize the brand. And in social engineering, the attackers have a very short period of time, only the reading of a mail most of the time. So the attackers can't use this method, but the marketing can.
No more questions. Last call. Over.
Thank you.
Thank you. Bon appétit.
Thank you. Just before you leave, information about the RAM session.
Yes, so let me
just 1
jump
minute
on the stage for that. Yes, sorry. So I think I realized that we forgot to tell you about the RAM session. So who doesn't know about what is a RAM presentation? Are you MP? Yeah, so okay, I'm gonna explain that to you. So it's a small presentation that you have like 3 minutes to discuss about one topic.
Or
any
5
topic.
perhaps.
Sorry?
Perhaps 5.
Yeah, 5 minutes. Sorry, I'm sorry. Yes,
3 or
5 minutes. And you can pick up whatever topic you want to discuss with us. And yeah, the exercise is you have a counter which is going to count down. And you're supposed to be done when the counter comes to 0. Okay. So if you want to present something, anything that you would like to present, you can come to us and register for a presentation. It can be anything funny or super serious. Okay. Thank you.
Okay, thank you.
just go for it. Don't think about what comes after or what came before. You just gotta bend your knees, take a deep breath, and jump. And you might think, what if I fall? Well, what if you don't? What if you fly?
Inscription is still open. We have up to now 5 presentations, right? Four,
Just
only 4. So it would be ideal to have like a number in between 8 and 10.
10,
and,
yeah. 10 would be great.
Yeah, yeah. So don't be shy. We won't bite you. We won't make have fun of you, and we won't be harsh, basically.
So please come and see us to register.
Okay.
Beers are offered.
Yeah, you have one extra beer if you extra beer if you present a representation. Okay. All right, so now it's time to have our second keynote of the day. So this one is going to be from Romain Kerr, who's a brand new assistant professor here in Toulouse. He's working for both INSA Toulouse and la CNRS, where he's doing his research. His main interests are related to wireless security. You're going to see that, and more especially about IoT devices and embedded system security. This guy essentially loves to hack around, mess around with embedded wireless stacks and playing with wireless protocols. You might already know him due to different works he has been publishing alongside, Damien, for a couple of them, I guess. And yes, at DEFCON, for instance, which is a great venue. Among them there is Wasabi, which is a cross-protocol pivoting attack, injectable. There is also Oasis, which is a defensive framework, wireless framework. Okay, so and then to finish is of course one of the main contributors of WAD that's going to be presented today, a new generation offensive framework for wireless protocols. And so Romain, we are already all ears. The floor is yours. Thank you.
Okay, let's go. Hi everybody. Thank you very much. So, I'm very pleased to be here, and today I will present to you a brief history of a very ambitious project named WAD. So, the subtitle of this talk is how we ended up creating a full ecosystem of open source tools for wireless security. So, briefly, let me introduce myself. So, I'm Romain Kerr. I'm a lecturer at INSA Toulouse and researcher at la CNRS in the Trust team. And yeah, my main research thematics are wireless security, embedded system security, especially in the context of the Internet of Things. And for this work, I have a co-author, Damien Coquille, also known as Virtual Labs. So unfortunately, he's not here today, but I'm sure he's watching, so hi Damien. And so Damien is security engineer at Coax Lab, developer of 2 major Bluetooth Low Energy offensive tools, Beetlejack and Beetlejuice, and his main research interests are wireless security, hardware security, and embedded system security. So, let me explain to you how all of this began. So, a few years ago, I was a small intern at la CNRS laboratory, and I was supposed to help Jonathan Roux, a PhD student, who was working on a protocol-agnostic intrusion detection system in the context of IoT. And my task at this time was to implement a set of realistic and diversified wireless attacks against various IoT wireless protocols to evaluate his intrusion detection system. So I started to take a look at the state of the art, and I quickly realized that it was a complete mess. So first of all, in terms of protocols, we have multiple heterogeneous protocols. So all of them are coexisting in the same environment. They are very fastly and very chaotically deployed in the wild. And all of them are engaged in a keen competition to win the IoT market. So manufacturers constantly release new features everywhere, and everything is evolving very fast. Then I started to take a look at the existing attacks, and I quickly noticed that there are a ton of different hardware that could be used to perform wireless attacks. So all these offensive hardwares are increasing in numbers and variety, And an interesting fact is that most of them are not suited for wireless security. So most of the time, security researchers write their own firmwares to add offensive capabilities. And of course, all these different offensive hardware provide different capabilities and features. So one of them could be used to sniff Bluetooth Low Energy, while the other could be used to jam Wi-Fi, and so on. On the software side, it's kind of similar. So they are also increasing in number and variety, and everyone reinvents the wheel constantly. So most of them are incompatible in terms of API. They are using different file formats. And most importantly, most of them focus on a specific hardware. Another big problem is that some of them are forced to use some high-level libraries, and these high-level libraries are often not designed for offensive security, so it leads to modifying some libraries and this kind of thing. So, if you want to perform various attacks against different wireless protocols, for example, to evaluate an intrusion detection system, it's kind of difficult. So, I started to write my own tool, and the idea was an attempt to improve this situation. So I started the development of a tool named Mirage. So the main guidelines of Mirage were to provide a unified API, to be as generic as possible, to have something which is modular and reusable, and to have ideally a low-level access to the software protocols. So my first attempt was this kind of architecture. So Mirage was split into different components. The first one is called the libraries, and it includes some low-level drivers to communicate with the various offensive hardware. On top of that, there was a generic communication architecture, allowing to harmonize the way to transmit and receive packets, and then the different protocol stack implemented in Mirage. Then there was the core component, handling mostly the module management and providing some concept like the background tasks and harmonizing the user interface. And finally, there were a set of modules that implemented some basic operation for a given protocol or some basic attacks like a man in the middle, jamming, and so on. If you want to customize the behavior of a specific module, there was also a concept called scenario, allowing to redirect the execution flow during the execution of a module to instrument it and customize its behavior. So it was the first attempt, but there were already a few interesting ideas. So Mirage was split into modules, and since every module was supposed to perform a basic operation or implement a simple attack, they could be combined together using a chaining operator if you want to build a complex attack workflow. So this chaining operator was very similar to a Unix pipe, and in this example, we are running first a scanning module in Bluetooth Low Energy, and we are using the output of this scanning module to advertise a new device with the second module, BLE ADV. Another interesting idea was to harmonize every packet from the different protocols into a single abstract representation. Then Mirage was built to provide a unified API to transmit and receive these different packets. So it was an attempt to harmonize the way to interact with different protocols. So, of course, there were a few limitations. So the native Unix pipe was not directly used. It was just a string with the modules and some pipes. So it leads to very complex command lines, especially if you want to combine a lot of modules. The abstract package representation lacked flexibility, leading to write a ton of translation layers. Some concepts were also very specific to Mirage, especially the scenarios, the tasks, and the modules. So if you want to use Mirage and do some advanced usage, you add a high learning curve. Components were also too tightly coupled, so it was hard to use a specific component outside of Mirage. And the most important problem was that it didn't change the way we write offensive firmwares. So if tomorrow you want to create a new firmware for supporting a new hardware, you also have a new driver to write in Mirage. Despite these limitations, the project had some success. So clearly, the tool has raised some interest in the community. Mirage was firstly publicly released at STIC 2019. At this time, it only supported Bluetooth Low Energy, and then a second release at ISSRE added support for Wi-Fi, Zigbee, and Structburst, Mozart, and basic infrared protocols. Then, during my PhD studies, I started to work on low-level attacks for various protocols, mainly Bluetooth Low Energy, but not only. And so I started to dive into the development of offensive firmware. So most importantly, Damien and I started working on two main system on chips, the NRF52 and the ESP32. So let me introduce my favorite system on chip, the NRF52. So it's provided by Nordic Semiconductor as a small dongle. So it's super cheap, less than 10 euro, and it's very hacker-friendly. It supports tons of different protocols. It provides a low-level access to the radio peripheral, and some old tricks presented by Travis Goodspeed a few years ago on the NRF24 still works. So Travis Goodspeed had identified that on the NRF24, it was possible to divert the use of the address register to simulate a kind of promiscuous mode for other protocols. And this hack still works on the NRF52. Last but not least, it has also a very fast switching time between the reception and the transmission. So if you want to perform some attacks that implies a very fast switching time, like reactive jamming, for example, it's very convenient. So I started at the beginning to write a BLE sniffer from scratch for this NRF52. And while I was implementing this sniffer, at some time I just tried to send randomly some packets while I was sniffing a connection, just to test if it would work or not. And surprisingly, it worked. So here I had a problem because if you know how a Bluetooth Low Energy connection works, it's not supposed to work. So typically, a Bluetooth Low Energy connection is composed of two nodes, a master and a slave. And the connection is divided into what we call connection event. At the beginning of each connection event, the master transmits a packet, and then there is a response from the slave. And then both nodes go to sleep mode until the next connection event. So it was a bit weird that by randomly injecting packets here, there was someone to listen to the packets. In fact, by carefully reading the specification, I finally understand why it was working. So in fact, it's a bit more complicated than that. There is a mechanism introduced by the specification named the window widening. So the idea is that the slave will listen a bit earlier than the ideal transmission instant of the master. And this mechanism is introduced to compensate the potential clock drifts between the two devices. So it opens the opportunity to take advantage of a race condition and to inject a packet at the very beginning of this window. So you can, as an attacker, manage to inject a packet before the legitimate master. So this attack, I called it the injectable attack, and it was published at DSN and implemented in Butterfly, the firmware for the NRF52. So over the time, I added more features. So I added the support for BLE central and peripheral support, so to act both as a master or a slave. And then I also implemented various other protocols, so Logitech Unifying, ZigBee, and also the opportunity for users to have access to a raw protocol support directly to the radio peripheral, so to basically to have access to modulatory input and demodulatory output. Then, a few years later, Damien and I started working on the ESP32. So the ESP32 system on chip is a very popular system on chip by Expressive Systems. It is very cheap. It includes Wi-Fi, Bluetooth Classic, and Bluetooth Low Energy. And it's very popular, especially in the maker community. So we wanted to understand how this system on chip was implementing its Bluetooth stack to see if we could divert this protocol stack and implement some low-level attacks. So typically, a Bluetooth Low Energy stack is divided into two main parts. First, you have the host part that handles the applicative and the security layers. And then you have the controller that handles the lowest layers, so the physical and the link layer. In between, you have an interface named the Host Controller Interface, or HCI. So let's see how ESP32 implements its BLE stack. So, on the top of the stack, you have the code written by the user, so the user application. Then you have NimBLE, which is used to implement the host part. So NimBLE is an open source stack. And then there is a virtual host controller interface, so it's only software here. And the interesting part is the controller part. So the controller part is divided into two main components. So the first one is running in software, and it uses some low-level functions that are stored in the internal ROM. And you also have a BLE coprocessor, so the BLE core, which interacts with the RF hardware. So, as a user, when you want to perform an action involving Bluetooth, for example, you will call a function in the NimBLE part. It will generate an HCI command, and this HCI command will then trigger an action on the controller part. So this action will not be called directly as a typical function, but there is an indirect call. So typically, in RAM, there is an array of function pointers, and these function pointers leads to the various low-level functions implemented in the internal ROM. So Expressive uses this mechanism to allow to modify the low-level functions. So typically, if you want to deploy a patch for one of these functions, you write your implementation in RAM, and you just have to overwrite the corresponding entry in the array of function pointers. So if we do that, we are now able to hook any function of the internal ROM, and so we have access to the low-level internals of the ESP32 BLE stack. Then we use this mechanism to perform some dynamic analysis, and we try to understand how the communication with the BLE core is realized. So, the ESP32 CPU communicates with the BLE core with two main mechanisms. So the first one is a few memory mapped registers. And then you also have another way to interact between these two components. It's a shared memory zone named the exchange memory. And it's what is the most interesting here, because if you analyze this exchange memory, you will see that it provides a very low-level control over the BLE core. So this exchange memory is divided into several parts. So the first one is a frequency table. So basically, it's an offset in frequency for every BLE channel. And you can then easily replace the frequency linked to a given channel. There is also some reception and transmission descriptors and some reception and transmission buffers, implementing the packets reception and transmission. And there is also the control structure. So the control structure is a section that contains various 16-bit registers that configure the modulator and the demodulator. So for example, one of these registers allows to change the data rate. Another one is used to modify the synchronization word. And you can also select some parameters that are related to the channel hopping mechanism of Bluetooth Low Energy. So let's summarize. You can hook every low-level functions in the internal ROM. You can arbitrarily change the data rate, the frequency, the synchronization word, and the timing. You got access to the demodulator output and the modulator input. So we can divert this ESP32 system on chip to add support for protocols that are not natively supported by the hardware. So let's see a small example. So here we are implementing the ANT+ protocol, which is a proprietary protocol very similar to Bluetooth Low Energy. So here we have an ANT+ watch from Garmin, and our ESP32 is mimicking an ANT+ heart rate monitor. So here you can see that it is correctly identified by the watch. And if we monitor the heart rate, you can see that it's a bit too high. So all these works lead to a set of new capabilities unlocked for these two system on chips. So by writing some low-level code for this system on chip, we were able to inject packets into BLE connections, to implement various multi-protocol primitives for ZigBee, ANT+, and so on, to add some attacks like continuous jamming, for example. And so here you have the two QR codes if you want to get access to the different firmwares. So at this point, a few observations. So Mirage, unfortunately, lacks some flexibility to perform this kind of low-level attacks. And if you need to play with low-level stuff like that, writing firmware is still the easiest way. But writing firmware is relatively costly, so you have to write it in C language, you have to know how embedded system works, and you have to perform some complex tricks to play with low-level stuff. On the other hand, transceiver can be pushed to their limits with funny hacks, and at this point, it allows to perform multi-protocol support and to divert very cheap hardware to add nice capabilities. So at this point, the question for me was, how can I do better than Mirage? So I did what every developer would do in this situation. I rewrote the entire project from scratch. Of course, with Damien. And so let's describe the tool of our dream. So in terms of protocol, we should be able to natively support multiple protocols. We should be able to easily extend the tool to add new ones. And of course, a lot of components could potentially be reused between different protocols. So it should facilitate code reuse when protocols share similarities. It should also provide a full control over the protocol stack, including the lowest layers. So you don't have to write firmware anymore. You can just do it from the host. On the hardware side, it should be natively compatible with the existing tools. So it should support your favorite offensive hardware, but ideally, it should also support future tools. So the idea is to considerably facilitate the development of new firmware, and of course, it should be adaptable to the various hardware capabilities. For the software part, it should be usable as a library in your own script or another program. It should provide a set of easy-to-use command line tools. It should allow to perform some complex workflows by chaining command line interface tools together. So it was a nice idea from Mirage. And it should be easy to extend, well-documented, and user-friendly. Ideally, it should also rely on robust and common tools and libraries like Scapy or Wireshark. So let's do that. Damien and I started working during my postdoctoral research when I was at Euricom. And we spent 2 years writing WAD, so this new ambitious project I want to present today. So what is the core idea behind WAD? It's a part of WAD named the WAD protocol. So the idea was to design an extensible host-device communication protocol. So it is well-defined. So we wrote it in protobuf, and we spent some time documenting it so it can be easy to understand with no ambiguities. It's generic, so it covers all the existing wireless capabilities, including the lowest one. It's modular, so it supports multiple wireless protocols, and it has been designed to be evolutive, so it can be easily extended and improved. Finally, it's user-friendly, and it comes with C, C++, and Python parsing libraries. Another key idea of WAD is to let the hardware do hardware stuff. So, of course, on the firmware side, you have some CPU and memory limitations. So the idea was to have only minimal logic on the firmware side. So basically, only the atomic wireless primitives and the time-critical operations that could not be realized from the host. Then we offload all the complexity to the host side. So everything else is implemented in the host part with the entire protocol stacks, the packet dissectors and builders, and of course, the attack and tools. So what happens when you plug supported hardware in WAD? So WAD will perform a device discovery. So it will transmit some messages, and thanks to these messages, it will be able to recover what is the version of the protocol supported by the hardware, what is the version of the firmware, this kind of information. And for every protocol which is supported by the hardware, it will then identify the capabilities that are available. So the idea is that on the host side, WAD is able to infer what API should be exposed to the user for this hardware. So today, we are supporting various different hardware. So, of course, the ESP32 and the NRF52 with our own firmwares. We also added support for some STM32 LoRaWAN transceivers. So for these different boards, they are natively supported by WAD, so they are implementing the support of the WAD protocol. But we also added some support for some tools that are very common and commonly used by security researchers working on wireless security. So for example, some ZigBee sniffers, the Yardstick one, allowing to interact with sub-gigahertz protocol, Logitech unifying dongle, the Bluetooth one, the Bluetooth low energy sniffer, and also typical Bluetooth HCI dongle. So for these devices, of course, they are not implementing WAD protocol, and we didn't want to modify the firmware. So we wrote some adaptation layers that convert the message from what protocol to the respective API of this hardware. So in terms of supported protocols, we spent a lot of time writing protocol stacks. So we expose a protocol named generic phi. So basically, the idea is to have access to the modulation and the raw stream as a modulator input and modulator demodulator output. And on top of that, we added support for Bluetooth Low Energy, N-struct burst, LoRaWAN, and .15.4. And based on these different protocols, Bluetooth Mesh, RF4CE, Zigbee, Meshtastic, and Logitech Unifying. So everything is entirely written in Python and based on Scapy, so very common technologies. They are designed to be easy to extend. So if you have your favorite protocol which is not supported, please do a pull request. And everything is based on a flexible stack model. So it's an abstract representation of the stack that allows to easily modify a specific layer. We added a feature to take protocol stack state snapshots. So it's very convenient if you want, for example, to do fuzzing. And it's easy to implement unit tests for the different components of the stack. Of course, WAD is way more than WAD protocol. So there is also, on the firmware side, the C and C++ parsing libraries that we call WADlib. And on the host side, it's a component named WAD client, which is composed of the Python client library that you can directly use in your scripts or programs, and a set of command line interface tools if you want to use WAD without writing a single line of code. And we reused the concept of pipe from Mirage, but we tried to improve it. So here, this is the real Unix pipe which is used. And so in this case, we have a first WAD tool that performs a connection. And once this connection is established, the WAD BLE central tool will perform a profile discovery to discover the services and characteristics of the device. In the middle, you can see WAD Shark that allows to easily monitor everything that occurs during the connection. So you can see in real time in Wireshark the packets involved in this operation. So just to briefly explain how it works. So the problem is that a pipe, by definition, is a unidirectional concept, but radio implies bidirectionality. So you have to transmit some commands to the radio, and the radio will send some responses. So Damien found a very cool design. The idea is that a reference to an Unix socket acting as a proxy to the radio will be propagated on the standard output between tools. And so a first tool will perform an action and use the radio. And when the action is successful, it will create the Unix socket acting as a proxy and propagate a reference to this Unix socket for the next tool on the standard output. So a very clever idea, and it allows to build complex attack workflow very easily, and it's way more easy to use than the Mirage version. So let's see a few demos. So here it's an example of a Zigbee tool. So we are using it in interactive mode. And in the corner, you can see two ESP32 that form a Zigbee network. So with this small tool, we are going to interact with this Zigbee network. So first, we scan the Zigbee network. Then we are going to join it. So you can see that we got the network key. And now we are going to perform a node discovery. So we identify that there is a coordinator and an end device. And for each node, we are going to discover the endpoints exposed by the node. So it allows us to identify that one of the nodes is a light device. So we are going to send a command to turn the LED on, and then another command to turn the LED off. So you can see that it's very easy to interact with a quite complex protocol like Zigbee without writing a single line of code. And of course, everything which is done here can be done from your own script if you want. So another small example. Let's imagine for a weird reason you want your Logitech unifying keyboard you want to use it with your smartphone. So unfortunately, your smartphone only supports Bluetooth. So let's build a Logitech unifying to Bluetooth Low Energy proxy. So we are going to use 2 dongles and WAD will emulate dongle for the Logitech unifying keyboard, and it will create a Bluetooth Low Energy keyboard on the other side. And we are going to forward the keystrokes from one wireless protocols to a completely different one. So let's do that. So here you can see the keyboard and the screen of the smartphone. So first we are going to synchronize our keyboard with our fake dongle. And here we spawn a fake Bluetooth Low Energy keyboard. So from the smartphone, we are going to pair with it. And once we have the connection and the BLE keyboard has been paired with the smartphone, we can just forward the keystrokes from the keyboard to the smartphone. And so we built very easily a simple proxy between 2 different protocols. So if you love domotics or things like that, it can be very useful for you. And finally, just to show you how powerful the concept of WAD protocol is. So in fact, it's a protocol, so we can just use it over TCP, for example. And so in this case, Damien and I are in 2 different cities, and I'm sharing my Bluetooth dongle with him over the internet. So now I do nothing, and he's going to connect to my dongle. So for him, it's exactly like it's a local device, but he is able to interact with my device that was shared using a tool named WAD server. And now he's going to turn the light bulb on and off. So yeah, nice and cool trick that we can do with WAD. Thank you. So, to conclude this talk, so since the release at DEFCON of WAD, we used it in a ton of cool stuff. So from research to pen tests, with teaching, challenges, and so on. So first, on the research side, it was used during an internship, the internship of Baptiste Boyer at Quarks Lab, under the supervision of Damien. So the idea was to write a fuzzer for the Bluetooth Low Energy applicative layers, the GATT layer especially. So Baptiste read the specification, identified several ambiguities, and wrote some scenarios to test these cases. And he managed to find several non-compliance and vulnerabilities with this fuzzer implemented with WAD. So some permissions bypass, some denial of service, and in the worst case, an out-of-bounds write. So CV has been assigned for Apache NIMBLE stack. And this talk was presented last year at Hardware I/O. It was also used in another project named Blue Scream. So the idea was to apply the screaming channel attacks to Bluetooth Low Energy. So a bit of context here. So screaming channel is side channel attacks that can be exploited at large distance. So it's linked to the fact that some mixed signal chips, so with analog and digital parts on the same dies, may intermodulate the leak signal with the RF carrier, and so it can propagate them at large distance. So the original attack by Camerati et al. Was demonstrated in laboratory conditions, and the question, one of the questions of the Pierre Ayoub PhD thesis was to know if it was realistic in real-life conditions, and especially if you use a real-life protocol. So basically, we showed the feasibility of retrieving the long-term key by exploiting the leak during the session key derivation